You see it every day. Perhaps you have some in your freezer right now. A single ice cube, floating in a glass of water. It is so familiar, so much a part of the background, that we rarely think about what it means. But this simple act of floating is a quiet departure from the way most things in the universe behave. It is an exception to a fundamental pattern of physics that governs almost everything else. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. And this exception is not just a curious detail. It is a silent architect of our world. The unusual property of this floating ice is what allows life to exist on this planet. If water behaved as most other substances do, if it followed the common rules, life as we know it would likely be impossible. The oceans might be solid blocks of ice, and the story of life would have ended long before it began. So, what is the quiet secret of water? What is this general rule that it does not follow? And how does this difference make our world habitable? Today, we are going on a journey into the water molecule itself. We will explore the subtle, elegant, and powerful reason why water expands when it freezes, why ice is less dense than water, and why this simple fact may be the most important anomaly on Earth. Before we can appreciate what makes water different, we first need to understand the rule. The one it does not follow. In the world of physics and chemistry, there is a predictable and nearly universal principle. When things get colder, they get smaller. When you cool down a substance, you are removing energy from its molecules. You can imagine a room full of people, moving and talking. They have energy, they take up a certain amount of space. Now, imagine the temperature in that room begins to drop. People will slow down. They will begin to gather closer together, packing themselves into a tighter, more compact group. The total space the crowd occupies shrinks. This is, in essence, what happens to atoms and molecules. As a liquid cools, its molecules lose energy. They move slower and pack more closely together. This causes the substance to become denser. Density is simply a measure of how much material is packed into a given space. As the molecules get closer, the same amount of mass fits into a smaller volume, and so, the density goes up. The colder it gets, the denser it gets. When that liquid finally freezes and becomes a solid, this trend usually continues. The molecules lock into a fixed, crystalline structure. For almost every substance, this solid structure is the most compact arrangement possible. Think of a neatly stacked pile of fruit at a market. There is very little wasted space. That is how most solids form, in a tight, efficient, high-density lattice. Molten metal, when it cools and solidifies, becomes denser. Liquid wax, when it hardens into a candle, shrinks and becomes denser. If you were to find a pool of liquid carbon dioxide, a block of dry ice would sink in it like a stone. This is the rule. The solid is denser than the liquid. This is a direct consequence of thermodynamics and the forces between molecules. It governs the behavior of metals, minerals, and the elements that make up our world. It is so consistent that our understanding of the material world is built upon it. And then there is water. Water seems to follow a different path. When water freezes, it does not shrink. It expands. It pushes outward, becoming less dense. A block of solid water, ice, does not sink in its own liquid. It floats. This is not a small difference. Upon freezing, water's volume increases by about 9%. It is as if that group of people, upon freezing, all decided to link arms, creating a formation that takes up far more space than their liquid state ever did. This single, quiet exception is what we are here to investigate. Why does water do this? The answer is not in some large, external force. It is hidden in the very shape and nature of the water molecule itself, in a special kind of connection that turns from a fleeting interaction in the liquid to a rigid, open, and life-giving structure in the solid. Before we look at the microscopic world, let's take a moment to understand the stakes. Let's do a thought experiment. What if water behaved normally? What if ice were denser than liquid water? Imagine a lake in the late autumn. The air grows cold, and the surface water begins to cool. If water were like any other liquid, this colder, denser water at the surface would sink. Warmer, less dense water from below would rise to take its place, where it too would cool and sink. This process, called convection, would continue, efficiently chilling the entire body of water from top to bottom. As winter arrives, the first ice crystals would form at the surface. But in this normal world, this ice would be denser than the water around it. So, it would sink. It would drift down and settle at the bottom of the lake. Then, the newly exposed surface water would freeze, and it too would sink. Layer by layer, from the bottom up, the lake would freeze solid. The entire body of water would become a single, lifeless block of ice. Any fish, amphibians, plants, or microorganisms living in that lake would be trapped and frozen. The ecosystem would be erased each winter. Life in freshwater environments, from small ponds to the Great Lakes and rivers, would be impossible. Now, extend that to a global scale. The polar oceans would freeze from the bottom up. The immense currents that circulate heat around our planet, driven in part by the dynamics of freezing and melting water, would stop. The climate system would be thrown into disarray. Without the insulating blanket of floating sea ice, the oceans would be unable to hold the vast amounts of thermal energy that moderate our planet's temperature. This could lead to extreme swings in weather. The very origin of life, which many scientists believe began in liquid water, might never have happened. Early Earth was a volatile place. A protective layer of floating ice on ancient ponds and seas could have shielded the delicate chemistry underneath from harsh radiation and other disturbances. Without this floating shield, the fragile beginnings of life might have been broken before they ever had a chance to form. Our world is blue precisely because of this unique property. The fact that ice floats is not a trivial detail. It is a quiet prerequisite for the complex, water-based life that defines our planet. So when we ask why ice is less dense than water, we are not just asking a simple physics question. We are asking what fundamental property of the universe allows us to be here. The answer begins with a journey into a single molecule of water. To understand water's unusual behavior, we must first understand the molecule itself. Let's zoom in, past the visible world, down to the atomic scale. Here, we find the water molecule, hydrogen oxide. The formula is simple. Two hydrogen atoms bonded to one oxygen atom. But this simple description hides an elegant structure. The atoms are not arranged in a straight line. Instead, the water molecule is bent. The two hydrogen atoms are attached to the oxygen atom at an angle of about 104.5 degrees, forming a V-shape. This bent shape is the first clue. The reason for it lies with the oxygen atom. Oxygen is highly electronegative. You can think of this as a kind of electron greediness. In the bonds it forms with the hydrogen atoms, the electrons are shared. However, the larger oxygen atom pulls these shared electrons closer to itself. This unequal sharing creates an imbalance within the molecule. Because the negatively charged electrons spend more time around the oxygen atom, that end of the molecule develops a slight negative charge. Consequently, the hydrogen atoms, with their electrons pulled partly away, are left with slight positive charges. This separation of charge, a negative pull at the oxygen and positive pulls at the hydrogens, makes water a polar molecule. It acts like a tiny, weak magnet. This polarity is the source of water's most important properties. And for our investigation, it is the reason for a special type of connection, the hydrogen bond. Because water molecules are like tiny magnets, they are attracted to each other. The slightly positive hydrogen atom of one water molecule is drawn to the slightly negative oxygen atom of a neighbor. This attraction is called a hydrogen bond. It's important to understand what a hydrogen bond is. It is not the strong covalent bond that holds a single water molecule together. A hydrogen bond is a force between molecules. It's much weaker, only about 1/20th as strong as a covalent bond. In liquid water, the scene is one of quiet, constant motion. The molecules are tumbling, spinning, and sliding past one another. In this state, hydrogen bonds are constantly forming, breaking, and reforming over incredibly short timescales. A molecule will form a fleeting connection with a neighbor, only to have it broken by thermal energy, before forming a new bond with another. The molecules are attracted to each other, which keeps water liquid and cohesive, but the bonds are too brief and disorganized to form a rigid structure. The molecules can still pack closely together, sliding into any available space. This is liquid water, a dynamic, densely packed, and disordered collection of molecules. But as we begin to cool this liquid, the movement begins to change. The molecules lose energy, and the fleeting connections start to become something more significant. This is where the story deepens, leading us to a very specific and important temperature. As we continue to cool our liquid water, we see something that is, at first, entirely normal. From a warm temperature down to about 4 degrees Celsius, or 39.2 degrees Fahrenheit, water behaves as expected. As the temperature drops, the molecules slow down. They move less, allowing them to pack more closely together. The volume decreases and the density increases. But then, at 3.98 degrees Celsius to be precise, something unusual happens. Water reaches its point of maximum density. Most liquids continue to get denser all the way to their freezing point. Water, however, hits its peak density and then begins to do the opposite. As you cool water below *4 degrees Celsius, from 4 degrees Celsius down to 0 degrees Celsius, it slowly begins to expand. It becomes less dense. What is happening in this narrow temperature range is a quiet, microscopic shifting of balance. Two opposing tendencies are at work. The first is the normal process of thermal contraction, slowing molecules trying to pack closer together, which acts to increase density. The second, and increasingly influential tendency, is the growing effect of the hydrogen bonds. As the molecules slow down even further, the hydrogen bonds start to last longer. They begin to assert their preferred geometry. A hydrogen bond is strongest when the hydrogen atom of one molecule points directly at the oxygen atom of another. Each water molecule can form 4 hydrogen bonds with its neighbors. The most stable arrangement for these 4 hydrogen bonds is a 3-dimensional shape known as a tetrahedron. Imagine the central oxygen atom with 4 arms pointing out to the corners of a pyramid. This tetrahedral arrangement is a very open, spacious structure. So, in the liquid water below 4 degrees Celsius, we see the beginnings of this ordering. Small, short-lived, ice-like clusters begin to form. These clusters are more ordered and take up more space than the surrounding, more disorganized liquid molecules. Above 4 degrees Celsius, the effect of thermal contraction is stronger. The slowing molecules pack tighter, and density increases. But as the temperature drops below 4 degrees Celsius, the formation of these more open, tetrahedral clusters starts to become more significant. More and more molecules spend more time in these expanded configurations. This expansion effect starts to overwhelm the contraction effect. The overall volume of the water begins to increase, and its density begins to decrease. The point at 4 degrees Celsius is the precise balance where the effect of thermal contraction is matched by the expansion caused by the pre-ordering of hydrogen bonds. Below this temperature, the hydrogen bonds take over, preparing the water for its final transformation. Some recent research suggests that under certain conditions, water may exist as a mixture of 2 distinct liquid states. a high-density, disordered liquid, and a low-density, structured liquid. The density anomaly we observe may be the result of the shifting balance between these two forms as the temperature changes. While this is still an active area of research, it reinforces the central idea. The unique nature of the hydrogen bond is quietly working against the normal rules of physics. We have arrived at the final stage of the story, the freezing point, 0 degrees Celsius. Here, the subtle balance we witnessed below 4 degrees becomes a complete shift. The movement slows to a near standstill. The molecules no longer have enough thermal energy to break the hydrogen bonds that have been forming. The fleeting clusters now lock into place. What was transient becomes permanent. The water molecules settle into the geometric arrangement dictated by their hydrogen bonds, forming a vast, rigid, and highly ordered crystalline lattice. The most common form of ice, the kind on frozen lakes, is called ice IH, where the H stands for hexagonal. This hexagonal structure is the direct expression of the tetrahedral bonding preference of each water molecule. As molecule after molecule settles into place, each forming 4 hydrogen bonds in that tetrahedral arrangement, they build up a repeating 6-sided pattern. This is why snowflakes have their beautiful 6-fold symmetry. It is a reflection of the underlying molecular structure. And here lies the solution to our mystery. This hexagonal lattice is remarkably open. It is full of empty space. The hydrogen bonds, in their search for the most stable arrangement, force the water molecules to hold each other at a distance, creating a structure that is significantly less dense than the jumbled state of liquid water. In liquid water, the molecules are like a disorganized pile of marbles in a jar. They can slide around and fill in the gaps, achieving a high density. In ice, those same molecules are now connected by rigid bonds at fixed angles, forming a spacious scaffold. The same number of molecules now takes up a much larger volume. As we've seen, this expansion is about 9%. And because density is mass divided by volume, this increase in volume leads to a decrease in density. The density of pure liquid water at its peak is 1 gram per cc. The density of ice is only about 0.917 grams per cubic centimeter. That difference is everything. It is the reason ice floats. It is the reason a massive iceberg floats on the surface of the ocean. The mystery is solved. Ice is less dense than water because of a combination of the bent shape of the water molecule and its polarity. This polarity creates hydrogen bonds. These hydrogen bonds favor a specific tetrahedral geometry. And this geometry, when locked into place during freezing, builds a spacious hexagonal crystal that takes up more volume than the disorganized liquid. It is a quiet, multi-step process that results in a profound exception to the way matter usually behaves. We have found the reason. We've journeyed to the molecular level and seen the secret of water's unusual property. But the story does not end there. Because now, we must zoom back out, from the molecule to the planet, and understand the deep consequences of this simple physical fact. We've already touched upon the most immediate one, the survival of aquatic life. Because ice floats, it forms an insulating layer on the surface of lakes, ponds, and seas. The water at the bottom of a frozen lake is often the densest, which, thanks to the density anomaly, is water at a relatively mild 4 degrees Celsius. The floating sheet of ice above acts like a cover, preventing the remaining heat in the water from escaping into the cold air. Under this protective icy blanket, an entire ecosystem can survive the winter. Fish and other organisms continue to live in the liquid water below. Without this floating shield, our planet's freshwater ecosystems would be barren. But the importance of floating ice extends far beyond local ponds. It is a critical part of the global climate. The vast ice sheets of the Arctic and Antarctic are not just static features. They are active components of Earth's climate system. These massive expanses of white ice act as giant mirrors. This property is known as albedo. Ice has a very high albedo, reflecting most of the sun's incoming radiation back into space. This helps to cool our planet, balancing the darker, more absorbent surfaces of land and ocean. As this ice melts, a feedback loop can be triggered, where darker ocean water absorbs more heat, causing more ice to melt. The stability of our current climate is deeply connected to the presence of these massive, floating shields of ice. Furthermore, the process of sea ice formation drives global ocean circulation. When seawater freezes, most of the salt is pushed out into the water below. This makes the water just beneath the ice extremely salty and therefore very dense. This cold, dense, salty water sinks, beginning a massive, planet-spanning circulatory system known as the thermohaline circulation. This system transports heat and nutrients all around the globe, shaping weather patterns and supporting marine life everywhere. The simple act of freezing water at the poles is the quiet engine for a system that helps regulate the entire planet. Even the ground beneath our feet is shaped by water's expansion. The process of frost wedging, where water seeps into cracks in rocks, freezes, and expands, is a slow, powerful geological force. Over long periods, this relentless cycle can split boulders and break down mountains, playing a role in creating soil and sculpting landscapes. Finally, this unique property of water has reshaped our search for life in the universe. We look with great interest at moons like Jupiter's Europa and Saturn's Enceladus. We believe they hide vast, liquid water oceans beneath their surfaces. These oceans can remain liquid, even in the cold of deep space, because they are protected by a thick, insulating shell of floating ice, the same principle that protects life in a winter pond. Water's anomaly doesn't just make Earth habitable. It creates potential habitats for life elsewhere in the cosmos. So, we return to where we began. A single ice cube floating in a glass. What was once a simple observation is now, hopefully, a source of quiet wonder. We have seen how the normal patterns of physics suggest that solids should be denser than their liquids. We have seen how water, thanks to the unique shape of its molecules and their polarity, follows a different path. We have uncovered the role of the hydrogen bond, that weak but persistent force that, in the cold, organizes the gentle chaos of liquid water into an elegant, open, and spacious hexagonal lattice. It is this crystalline structure that causes water to expand upon freezing, to become less dense, and to float. And we have seen the profound consequences of this one simple anomaly. From protecting life in a frozen lake to helping regulate the planet's climate and guiding the search for extraterrestrial life, the fact that ice floats is one of the most important and life-giving properties of any substance we know. The next time you place an ice cube in a drink and watch it float to the surface, perhaps take a moment. Appreciate the quiet exception taking place in your glass. You are witnessing an everyday occurrence that is also a silent pillar of our world, and a key to life itself. If this kind of calm exploration into the world around us helps you unwind, consider liking the video and subscribing to the channel. And let us know in the comments below, what other everyday phenomena have you always wondered about? Thanks for watching. The bizarre reason ice defies gravity. In the known universe, the laws of physics are remarkably consistent. Heat a substance, and its atoms move apart. Cool it, and they draw closer together, becoming denser. This principle is so fundamental that for nearly every substance, its solid form is denser than its liquid form. A piece of solid iron will sink in molten iron. A piece of solid wax sinks in liquid wax. But here, on our own planet, the most common substance on its surface quietly disobeys this rule. Pause. When you place solid water into liquid water, it floats. It's an observation so commonplace we barely register its strangeness. But it represents a profound deviation from the norm. The reason for this behavior is not a trick. It is a secret hidden at the molecular level. A secret that rearranges the very architecture of water and, in doing so, makes complex life on Earth possible. This is a journey into that secret, into the strange, counterintuitive, and elegant reason that ice defies a seemingly universal rule. The universal rule and the lone exception. To grasp how unusual it is that ice floats, we first need to understand the fundamental principle it breaks. It all comes down to the concept of density. Density is a measure of mass contained within a certain volume. Imagine two identical containers. One is filled with pillows, the other with books. While their volume is the same, the container of books has more mass and is therefore denser. This applies to everything, from planets to particles. In the world of liquids and solids, temperature is the primary driver of density. When a substance is heated, its molecules gain kinetic energy. They vibrate more rapidly and push against each other, increasing the space between them. The same mass now occupies a greater volume, and so its density decreases. Conversely, as a substance cools, its molecules slow down. They draw closer together, occupying less volume for the same mass, and density increases. This is the universal rule. As things get colder, they become denser. This is why for virtually any substance, the solid state, where molecules are locked in place, packed as tightly as possible, is its densest state. A solid will sink in its own liquid. But then, there is water. Water follows this rule, but only to a point. As you cool liquid water, it predictably becomes denser. Its molecules slow, and they pack closer together. But then, something extraordinary happens at 4 degrees Celsius, or about 39.2 degrees Fahrenheit. At this temperature, water reaches its maximum density. If you continue to cool it past this point, it begins to do the opposite of what it should. It starts to expand. The molecules begin to push apart, and the water becomes less dense. This property, known as the anomalous expansion of water, was a subject of scientific inquiry as early as the 18th and 19th centuries. As the temperature drops from 4 degrees Celsius down to 0 degrees Celsius, the point of freezing, the water continues to expand. By the time it transitions into solid ice, its volume has increased by about 9%. This significant increase in volume means that ice is roughly 9% less dense than the cold liquid water from which it formed. And that is why ice floats. It is a physical property that sets water apart. While a few other substances like silicon, gallium, and bismuth also form solids that are less dense than their liquids, water's behavior has uniquely life-altering consequences. This seemingly small act of defiance is not just a curiosity, it is one of the most critical properties of matter in the universe. To understand why it happens, we have to move from the scale of ice cubes to the world of molecules, where a special connection rewrites the rules. The molecular dance, polarity and the hydrogen bond. To find the origin of ice's unusual behavior, we have to look at the water molecule itself. Its formula, H2O, describes two hydrogen atoms bonded to one oxygen atom. The key, however, is in their arrangement. The molecule is not linear, it is bent, giving it a distinctive shape. This shape is just the beginning. The true secret lies in a property called polarity. Within the water molecule, electrons are shared between the atoms, but they are not shared equally. The oxygen atom is highly electronegative, meaning it has a stronger pull on these shared electrons. It draws them closer to its own nucleus, and away from the hydrogen atoms. This unequal sharing creates a slight imbalance of charge. The oxygen end of the molecule develops a slight negative charge, while the two hydrogen ends are left with slight positive charges. The molecule as a whole is neutral, but it has a positive side and a negative side. It is a polar molecule. This polarity allows water molecules to form a special type of connection with each other, the hydrogen bond. The slightly positive hydrogen end of one molecule is attracted to the slightly negative oxygen end of a neighbor. This electrostatic attraction is what we call a hydrogen bond. It is not a true covalent bond like those holding the molecule together. It is much weaker, about 10 to 20 times weaker. In liquid water, these hydrogen bonds are in a constant state of flux. They form, break, and reform trillions of times per second in a chaotic, disorganized dance. This constant motion allows the molecules in liquid water to slide past one another and pack together quite closely, even with their disorganized structure. The story of floating ice begins when this molecular dance slows down. As water cools, the molecules lose kinetic energy. They move less frantically. This gives the hydrogen bonds, previously so fleeting, a chance to exert a greater influence. The dance becomes less chaotic and more organized. As the temperature approaches 4 degrees Celsius, two competing forces are at work. The first is the normal process of cooling, which tries to pack the molecules closer together, increasing density. The second is the ordering influence of the hydrogen bonds, which try to arrange the molecules into a more structured, but more open, formation. At 4 degrees Celsius, these two forces reach a balance, and the water molecules achieve their tightest possible packing, their maximum density. Then, as the water cools from 4 degrees Celsius to 0 degrees Celsius, the second force begins to win. The stabilizing hydrogen bonds start to lock the molecules into place, halting their chaotic movement. They force the molecules to arrange themselves into a very specific, highly ordered pattern. This is the moment everything changes. The crystal palace, unveiling the structure of ice. When water freezes at 0 degrees Celsius, the molecular dance concludes in an elegant, structured form. The hydrogen bonds become stable, locking each water molecule into a fixed position relative to its neighbors, creating a crystal. The form of ice we encounter every day is known as ice IH, where H stands for hexagonal. Its structure, first glimpsed through X-ray crystallography in the 1920s, is a repeating three-dimensional lattice. Later, in 1935, chemist Linus Pauling proposed the precise arrangement of the protons within this structure. In this lattice, every oxygen atom is connected to 4 others through hydrogen bonds, forming a geometric shape called a tetrahedron. Imagine a central water molecule. Its 2 hydrogens point toward the oxygen atoms of 2 other molecules, while its own oxygen atom attracts the hydrogens of 2 more. This creates a perfect tetrahedral arrangement with 4 neighbors. These tetrahedrons then link together to form a series of interlocking hexagonal rings. Layers of these rings stack on top of one another, like a 3-dimensional honeycomb. This highly ordered, symmetrical structure is what gives snowflakes their characteristic 6-pointed symmetry. The consequence of this beautiful, organized structure is profound and counterintuitive. It takes up more space than the chaotic jumble of liquid water. The rigid hexagonal lattice of ice is remarkably open. The hydrogen bonds lock the molecules at a fixed distance from each other, creating significant empty space within the crystal. Because of this open lattice, the same number of water molecules, the same mass, occupies a larger volume when frozen than it does as a liquid. And since density is mass divided by volume, an increase in volume with the same mass results in a decrease in density. The density of liquid water at 4 degrees Celsius is approximately 1 gram per cc. The density of ice IH at 0 degrees Celsius, however, is only about 0.917 grams per cubic centimeter. This difference means ice is about 9% less dense than the water from which it formed. This is the definitive, molecular reason ice floats. It is less dense than the liquid surrounding it. According to Archimedes' principle, an object in a fluid is buoyed by a force equal to the weight of the fluid it displaces. Because ice is less dense, the water it displaces weighs more than the ice itself, creating a net upward force. This is why an iceberg has approximately 90% of its mass submerged, with only the tip visible. It is interesting to note that this hexagonal structure isn't the only form ice can take. Under conditions of extreme pressure, Scientists have identified at least 19 different phases of ice. Some of these, like Ice 3 and Ice V, are denser than liquid water and would sink. But here on Earth, under our atmosphere, we get the one form, Ice IH, that floats. And the consequences of this are world-shaping. A world without floating ice. We have unraveled the molecular mechanism. But what is its significance? To answer this, we can perform a thought experiment. What would our world look like if water behaved normally, and its solid form was denser than its liquid? In that world, as winter arrived, the first ice crystals forming on the surface of a lake would sink. The newly exposed surface water would then freeze and sink in turn. This process would continue, layer by layer, until entire lakes, rivers, and even parts of the ocean were frozen solid, from the bottom up. The consequences for life would be catastrophic. Aquatic organisms would be crushed or frozen. Instead of a winter refuge, bodies of water would become solid blocks of ice. When summer returned, only the very top layer would melt. The deep ice, shielded from the sun, might never thaw, accumulating year after year. This could trigger a runaway cooling effect, fundamentally altering the global climate. It is unlikely that complex life could have ever flourished in the way that it has. But thankfully, we live in this world. In our world, as a lake cools, the densest water at 4 degrees Celsius sinks, until the entire lake is 4 degrees Celsius. Then, as the surface water cools further towards 0 degrees Celsius, it becomes less dense and stays at the top. When it freezes, the resulting ice sheet remains on the surface, forming an insulating blanket. This layer protects the liquid water below, allowing aquatic life to survive the winter in a stable environment. This property shapes our entire planet. The vast, floating polar ice caps reflect enormous amounts of solar radiation back into space, a phenomenon known as the albedo effect, which helps to regulate Earth's temperature. The expansion of water as it freezes is also a primary driver of geological erosion. Water seeps into the cracks of rocks and expands with immense force upon freezing, a process called frost wedging that can, over eons, break down mountains. From the survival of a single fish to the shape of our landscapes and the stability of our climate, it all traces back to this one bizarre fact. It all comes back to those polar molecules and the hydrogen bonds that arrange them into an elegant, open, and gravity-defying crystal. So, the next time you place an ice cube in a glass and watch it float, remember that you are not just witnessing a simple event. You are seeing a consequence of quantum mechanics and molecular geometry. You are seeing the result of the water molecule's bent shape, its polarity, and the power of the hydrogen bond to build a crystalline palace so spacious that it becomes lighter than its own liquid. It's a reminder that the most fundamental properties of our world often arise from invisible, intricate details. This simple anomaly, this deviation from the rules, is precisely what creates the conditions that allow for the complex and wonderful history of life on Earth. It is one of the universe's most important secrets, hidden in plain sight. Water's hidden superpower you never knew about. The story of water seems, at first, a simple one. We learn its chemical name in school, hydrogen oxide. 2 parts hydrogen, 1 part oxygen. A basic recipe for the most essential substance on our planet. We see its formula drawn as a V-shape, a basic stick figure drawing in the grand textbook of the universe. It seems almost accidental, an afterthought of chemistry. But what if I told you that this specific shape is no accident? What if it is a quiet, deliberate design that grants water a hidden power? A power so profound that it prevents our oceans from freezing solid from the bottom up, acting as a shield for all the life that thrives in the dark, cold depths below. This is not a story about magic. It is a story of geometry. It's about an angle, a specific number, 104.5 degrees. That dictates the fate of our world. This is a journey to discover the secret of water's deceptively simple structure. To understand why this hidden power is the fundamental reason life, as we know it, can even exist. Prepare to look at a simple glass of water and see the entire history of life on Earth reflected within it. The anomaly of the ice cube. Let's begin with a phenomenon so common, we rarely give it a second thought. You drop ice cubes into a drink, and they float. It feels entirely normal. It is what we expect. But have you ever paused to truly question why? Why does the solid form of water float on its liquid form? This question sounds simple, but the answer is key to everything. For nearly every other substance in the universe, this does not happen. From iron to candle wax to carbon dioxide, the solid form is denser than its liquid. If you were to pour molten iron into a vat and add a solid iron cube, it would sink instantly. A block of frozen nitrogen would sink in a pool of liquid nitrogen. This is the rule of physics. As things grow colder, their atoms slow, vibrate less, and pack together more tightly. More mass in the same space means higher density. The solid sinks. Water breaks this rule, and it does so spectacularly. When water freezes, it performs a quiet act of rebellion against physics. It expands. It becomes less dense. This is why a can of soda forgotten in a freezer will burst, its expanding contents overwhelming the aluminum walls. And it's why icebergs, those majestic mountains of frozen water, bob serenely in the polar oceans instead of plunging to the seabed. Now, let us run a thought experiment. Imagine a world where water behaved normally, where ice was denser than liquid water. What would happen in our lakes, rivers, and oceans as winter arrived? As the air temperature fell below freezing, the surface water would cool. At 0 degrees Celsius, it would freeze into ice. But in this alternate reality, that new ice would be denser than the water beneath it. And so, it would sink. As it settled on the bottom, a new layer of water would be exposed to the freezing air. It, too, would freeze and sink. Layer by layer, ice would accumulate from the bottom up. The process would continue relentlessly. Without a floating layer of ice to serve as an insulator, the entire body of water would be exposed to the harsh winter cold. Before long, the lake would freeze solid, from the floor to its surface. Any fish, any turtle, any plant, all aquatic life, would be crushed and frozen in a monolithic block of ice. Winter would mean total extinction. Our oceans would face the same fate. Ice forming in the polar regions would sink, accumulating on the ocean floor and displacing warmer bottom water, causing massive, unpredictable shifts in global climate. Over geological time, the planet's deep oceans could fill with sunken ice, creating a frozen, lifeless abyss from which the world might never recover. Life, which we believe began in water, might never have had the chance to begin at all. The single fact that ice floats creates a protective blanket over our planet's waters. This shield insulates the liquid below, allowing life to thrive in the relatively stable temperatures of the deep. Ecosystems endure, and the planet's climate remains in a delicate, life-sustaining balance. So, the trivial question of a floating ice cube becomes one of the most important questions we can ask. Why is water the great exception? What gives it this life-saving power? The answer is not found in the vastness of the ocean, but in the unseen world of the infinitesimally small. The secret lies within the architecture of a single water molecule. The search for a culprit, down to the molecule. To understand this global phenomenon, we must shrink our perspective. Dramatically, we must go from the scale of oceans down to the scale of atoms. The reason for everything we've just discussed is hidden in the design of a single molecule of water. We all know the formula: hydrogen oxide. First pieced together in the late 18th century by chemists like Henry Cavendish and Antoine Lavoisier, it was confirmed by 1811 that water was not an element, but a compound made of 2 hydrogen atoms for every 1 oxygen. Now, if you were to sketch this molecule without any prior knowledge, you might draw it in the simplest way: a straight line. HOH. symmetrical and balanced. It seems logical. Carbon dioxide, another molecule fundamental to life, arranges itself in this exact linear fashion. But water does not do that. Water is different. Through decades of meticulous investigation, using techniques like X-ray diffraction which can probe the very structure of matter, scientists confirmed something remarkable. The water molecule is not linear. It is bent. The two hydrogen atoms are pushed to one side, creating a distinct V-shape, as if the oxygen atom is the vertex and the hydrogens are the tips. This is not a minor detail. This bent shape is the entire story. If the water molecule were linear, ice would sink, and a living planet might be impossible. The difference between a watery, living world and a frozen, dead one comes down to a simple geometric fact: water is bent. So the question deepens. It's no longer just, why does ice float? Now, it is, why is the water molecule bent? What force acts on these three atoms, pushing them out of a straight line and into this specific, life-giving configuration? Is it a random quirk of nature, or the result of a fundamental principle governing how atoms assemble the world? To find the answer, we have to go deeper still. Past the atoms themselves and into the invisible ocean of particles that surrounds them, the electrons. The secret of water's shape is written in the language of electric charge and quantum mechanics. The V-shape is not an accident, VSEPR theory. The force that bends the water molecule is one of the most fundamental in nature: repulsion. Just as like poles of two magnets push each other away, objects with the same electrical charge repel one another. The architects of the water molecule's shape are its electrons, the negatively charged particles orbiting the atomic nuclei. To understand this, we introduce a beautifully simple, powerful idea called VSEPR theory: valence shell electron pair repulsion. The concept is incredibly intuitive. It states that groups of electrons in the outer shell of an atom, the valence shell, will arrange themselves in three-dimensional space to be as far apart from each other as possible, minimizing the repulsion between them. Imagine you have four balloons and tie their ends together. They don't lie flat. They naturally form a three-dimensional shape called a tetrahedron, a pyramid with a triangular base. This is the most stable arrangement, where each balloon is as far from the others as it can be. The angle between the center and any two balloons is about 109.5 degrees. This shape is a fundamental geometry in chemistry. Now, let's apply this to our water molecule. The central atom is oxygen, which has 6 electrons in its outer shell. 2 of these electrons form bonds with the 2 hydrogen atoms. These are called bonding pairs. But that leaves 4 electrons, or 2 pairs, that are not involved in bonding. These are called non-bonding pairs, or lone pairs. So, around the central oxygen atom, we have 4 distinct groups of electrons: 2 bonding pairs and 2 lone pairs. According to VSEPR theory, these 4 groups repel each other and arrange themselves into a tetrahedron. But here is the crucial twist. Not all electron pairs repel with the same force. The lone pairs belong only to the oxygen atom. They are not stretched out in a bond between 2 atoms. Held more closely to the oxygen nucleus, they take up more space and exert a stronger repulsive force than the bonding pairs. They have a dominant repulsive influence in the molecule's structure. In a perfect tetrahedron, like methane, carbon tetrahydride, with 4 identical bonding pairs, the angle is 109.5 degrees. But in water, the 2 powerful lone pairs push down on the 2 weaker bonding pairs. They squeeze the HOH bond, compressing it. The angle is forced to shrink from the ideal 109.5 degrees down to a much smaller, more specific angle, approximately 104.5 degrees. And there it is, the origin of the V-shape. It is not an accident. It is the direct, predictable result of the unseen negotiation between 4 groups of electrons, a subtle difference in repulsion that locks the water molecule into its characteristic bent geometry. This shape, forged by repulsion, is the first critical step. The next is to understand what this bent shape does to the molecule's personality. The superpower of polarity. The bent shape of the water molecule is the first domino. The next is a property called polarity, and it's what turns water from a simple molecule into the foundation for life. Polarity arises from another fundamental property of atoms: electronegativity, a measure of how strongly an atom pulls on electrons in a bond. In water, we have oxygen and hydrogen. When it comes to electronegativity, oxygen has a powerful hunger for electrons. Hydrogen does not. When oxygen bonds with hydrogen, they are meant to be sharing electrons. But it is not an equal sharing. The greedy oxygen atom pulls those shared electrons much closer to its own nucleus. The result is a separation of charge. Because the negative electrons spend more time around the oxygen atom, that end of the molecule develops a slight negative charge, delta minus. Conversely, with electrons pulled away, the hydrogen atom's positive nuclei are more exposed, giving their side of the molecule a slight positive charge, delta plus. Each OH bond, then, is a tiny electrical dipole, a positive end and a negative end. Here is where the molecule's shape becomes absolutely critical. Let's return to our thought experiment where water was a linear molecule, HOH. It would still have two polar bonds. The oxygen would be negative, and the two hydrogens would be positive. But due to the symmetry, the positive charge on the left would pull in the exact opposite direction of the positive charge on the right. The partial charges would cancel each other out. The molecule as a whole would be nonpolar, just like carbon dioxide. But water isn't linear. It's bent. Because of that 104.5-degree angle, the two partially positive hydrogen atoms are on the asterisk same side of the molecule. Their positive charges combine to create a distinct positive region. On the opposite side, where the lone pairs reside, the oxygen atom forms a distinct negative region. The molecule now has a positive pole and a negative pole. It has become a tiny magnet. This is what we mean when we say water is a polar molecule. This polarity is arguably water's most important trait. It makes water the universal solvent. When you stir salt into water, the polar water molecules surround the salt's ions. The negative oxygen ends swarm the positive sodium ions, while the positive hydrogen ends surround the negative chloride ions, gently pulling the crystal apart. This ability is why our blood can carry nutrients and our cells can function. Life is a chemical process, and water is the medium in which it happens. But the story does not end here. This polarity, born from the molecule's bent shape, leads to one final, crucial property. A special kind of connection that gives water its most startling and life-affirming power. The hydrogen bond network. We now have the pieces in place. A molecule that is bent and therefore polar, with a negative end and a positive end. What happens when you put billions of these tiny molecular magnets together? They stick to each other. The partially positive hydrogen of one water molecule is attracted to the partially negative oxygen of a neighbor. This specific attraction is called a hydrogen bond. A hydrogen bond is an intermolecular force, a force between molecules. It's much weaker than the covalent bonds holding a single water molecule together, but what these bonds lack in individual strength, they make up for in numbers. Each water molecule can form up to 4 hydrogen bonds with its neighbors. In liquid water, this network of hydrogen bonds is in a constant, chaotic state of flux, forming, breaking, and reforming. This vast, ever-shifting network is what gives liquid water its strange and wonderful properties. It's the reason for surface tension, the elastic-like skin on water's surface that allows insects to walk on it. It is also responsible for water's incredibly high specific heat capacity. It takes a huge amount of energy to break these bonds and raise water's temperature. This property makes the oceans a global thermostat, moderating our climate. It's also why our bodies, being about 60% water, can maintain a stable internal temperature. These properties are all direct consequences of hydrogen bonding. Hydrogen bonding is a consequence of polarity. And polarity is a consequence of the bent shape. A beautiful cascade of cause and effect, starting with two lone pairs of electrons. But to explain our original mystery, the floating ice cube, we must slow this molecular dance down and watch what happens when those fleeting connections become permanent. The grand finale, the crystal lattice. As liquid water cools, its molecules slow down. The frantic dance of hydrogen bonds calms. At 4 degrees Celsius, water reaches its maximum density. Below this temperature, the true strangeness begins. As the temperature approaches freezing, the molecules have so little energy they can no longer resist the geometric demands of the hydrogen bonds. They begin to lock into place. This is where the 104.5-degree angle reveals its ultimate purpose. Because of this rigid, bent structure, the molecules cannot simply pack together tightly. To satisfy the demands of hydrogen bonding, they are forced to arrange themselves in a very specific, orderly, and surprisingly open pattern. They form a three-dimensional, hexagonal crystalline lattice. Imagine dancers in a grand hall, each required to hold hands with 4 other dancers, but with their arms locked at a specific, awkward angle. To maintain their connections, they would have to stand far apart, creating a spacious arrangement. This is what happens when water freezes. Each molecule forms 4 hydrogen bonds with its neighbors, creating a rigid, repeating tetrahedral network. This crystalline structure is beautiful. It gives snowflakes their 6-sided symmetry. But more importantly, it is filled with empty space. The molecules in this rigid lattice are held further apart on average than they are in the disorderly chaos of liquid water. And that is the final piece of the puzzle. More space between molecules means fewer molecules in a given volume. Fewer molecules in the same volume means lower density. Ice is less dense than liquid water because the rigid, open lattice created by hydrogen bonds takes up more space. The 104.5-degree bend dictates the geometry of the hydrogen bonds, which in turn dictates the open structure of ice. It is a direct chain of command from the subatomic to the macroscopic. The world we inhabit. Let us return, finally, from the microscopic world of electron pairs and bond angles to the world we can see and touch. The world of frozen lakes and vast, floating ice shelves. Because ice is less dense than water, it floats. As winter descends on a lake, a layer of ice forms on the surface. It does not sink. It stays on top, creating a solid cap that separates the water below from the frigid air above. Ice is a poor conductor of heat, so this layer acts as an excellent insulator, a blanket for the lake. Beneath this shield, the rest of the lake remains liquid. Aquatic life, from microorganisms to fish, can survive the winter in this insulated sanctuary. The entire ecosystem is preserved, ready to reawaken in the spring. This simple act of floating ice is the reason life can persist in temperate and polar regions. It is the reason our planet did not lock itself into a permanent ice age eons ago. The anomalous behavior of this single substance is the bedrock upon which the stability of our planet's climate and the survival of its ecosystems are built. This entire chain of consequence begins with one fact: the water molecule is bent. A shape dictated by the repulsion of its own electrons. This bent shape creates polarity. Polarity allows for hydrogen bonds. And hydrogen bonds force ice into an open, low-density crystal lattice that floats. That is how life can exist. This incredible story is hidden in every drop of water, every snowflake, every ice cube. Science is full of these hidden narratives, where simple questions lead to profound truths about how our universe works. If you enjoyed this journey into the secret life of water, consider subscribing. We dive into stories like this every week. We'd love to hear your thoughts in the comments. What other everyday phenomena do you think hold deep, scientific secrets? So the next time you look at a glass of ice water, take a moment. It is not just a simple V shape by accident. It is a structure forged by the fundamental forces of quantum mechanics. You're looking at a substance whose precise 104.5-degree angle is a pillar of life on Earth. You are witnessing a hidden power in action, the quiet, constant miracle of floating ice. A power that turns a simple molecule into the guardian of our planet, protecting the very existence of every living thing in the water below, and by extension, life itself. The bizarre reason ice floats. We see it happen so often, it can seem unremarkable. A cube of ice bobs at the surface of a drink. A lake in winter freezes over, forming a solid sheet across the top. This behavior is so familiar that we rarely consider its implications. But in the context of chemistry and physics, it is a significant anomaly. The rules that govern nearly every other substance in the universe suggest this shouldn't happen. If water behaved like most other compounds, ice would be denser than its liquid form. As a lake cooled, the ice would form at the surface and then sink. More ice would form, and it too would sink. Layer by layer, from the bottom up, the entire body of water would freeze solid. This process would occur every winter, and the aquatic life within those waters would not survive. This outcome is what the standard principles of physics would predict. But it doesn't happen. This is prevented by a peculiar and essential property of water. The fact that ice floats is an exception to a nearly universal rule, and it's an exception that allows for the persistence of life in our world. It begins with a simple observation. To understand why ice floats, we first need to understand the rule that water breaks. We need to examine the concept of density. Density is a measure of mass within a certain volume. A useful way to think about it is in terms of molecular packing. The state of a substance, solid, liquid, or gas, is determined by the energy and movement of its molecules. In a gas, molecules have a great deal of energy. They are spread far apart, moving rapidly and randomly. This is the least dense state. As a gas cools, its molecules lose energy and slow down. The weak attractions between them begin to take hold, and they condense into a liquid. In the liquid state, the molecules are much closer together, able to move past one another but still in constant contact. They are far denser than a gas, but their arrangement is still disordered and inefficient. When the liquid cools further, more energy is removed. The molecules slow until the forces between them lock them into fixed positions. They can no longer slide past each other, they can only vibrate in place. They have formed a solid. For nearly every substance, this solidifying process represents the most efficient packing arrangement possible. The molecules pull in as tightly as their geometry allows, minimizing the space between them. More molecules are packed into the same volume compared to the liquid state. The result is that the solid is denser than the liquid. We can see this with everyday materials. Liquid wax from a candle cools and hardens into a smaller, denser solid, often creating a dip in the surface as it contracts. If you were to drop a piece of solid wax into molten wax, it would sink. The same is true for most metals. A solid steel ball dropped into a crucible of molten steel will sink to the bottom. From iron to wax, the solid form is the densest form. This is the predictable behavior of matter. Water, however, follows a different set of principles. When you place an ice cube in a glass of water, the solid floats in the liquid. According to the general rule, the solid should be denser and should sink. But it does not. Ice is approximately 9% less dense than liquid water. This means that when water freezes, it expands, taking up more space than it did as a liquid. This is the opposite of what we observe in almost all other substances. This property is known as the anomalous expansion of water. The behavior doesn't just begin at the freezing point. For most liquids, cooling them results in a steady increase in density until they solidify. Water follows this pattern for a time. As it cools, it becomes progressively denser, but only until it reaches a specific temperature, 4 degrees Celsius or 39.2 degrees Fahrenheit. At this point, water achieves its maximum density. As it is cooled further, from 4 degrees down to 0 degrees Celsius, it begins to expand. It becomes less dense as it gets colder. The molecules are losing energy, yet they are beginning to push farther apart, even before they have locked into the solid structure of ice. This point of maximum density at 4 degrees Celsius is a critical piece of evidence. It suggests that the reason for ice's buoyancy isn't an abrupt change at the moment of freezing, but part of a process that begins within the liquid itself. The explanation for this behavior is found at the molecular level, in the structure of the water molecule and the forces that act between its neighbors. To understand how billions of water molecules behave together, we first need to understand the structure of a single hydrogen oxide molecule. At its center is one oxygen atom bonded to 2 hydrogen atoms. An atom's chemical behavior is dictated by its electrons. Oxygen is a highly electronegative element, meaning it has a strong attraction for the electrons it shares in a chemical bond. Hydrogen's electronegativity is significantly lower. This difference is the most important fact about the water molecule. The oxygen atom forms a covalent bond with each of the 2 hydrogen atoms. In a covalent bond, atoms share a pair of electrons. It's a strong intermolecular force that holds the molecule together. However, because of oxygen's high electronegativity, this sharing is unequal. The shared electrons are pulled much closer to the oxygen atom's nucleus. Since electrons are negatively charged, their tendency to cluster around the oxygen atom creates a charge imbalance. The oxygen end of the molecule develops a slight negative charge, while the 2 hydrogen atoms, with their electrons pulled away, develop a slight positive charge. This makes water a polar molecule, with 2 distinct, oppositely charged ends. Its shape is also a critical factor. The 2 hydrogen atoms do not sit on opposite sides of the oxygen atom in a straight line. The oxygen atom has 2 lone pairs of electrons not involved in bonding. These negatively charged lone pairs repel the electrons in the covalent bonds, forcing the hydrogen atoms closer together and creating a bent, V-shaped structure. The angle of this bend is approximately 104.5 degrees. This bent shape ensures that the positive and negative poles are permanently separated. Water is asymmetrically polar. This structure is the key to all of its unusual properties, including why ice floats. A single water molecule, then, is like a small, bent magnet. When many of these molecules are brought together, the positive end of one is attracted to the negative end of another. The partially positive hydrogen atom of one molecule feels an attraction to the partially negative oxygen atom of a neighbor. This electrostatic attraction between separate molecules is called a hydrogen bond. It is important to distinguish this from a covalent bond. The covalent bonds that hold a water molecule together are intermolecular forces, and they are very strong. Hydrogen bonds are intermolecular forces, acting between molecules. They are much weaker, only about 1/20th as strong as a covalent bond. They are strong enough to influence how water molecules arrange themselves, but weak enough that they can be constantly formed and broken. Each water molecule has the capacity to form 4 hydrogen bonds with 4 different neighbors. Its 2 positive hydrogen atoms can bond to the oxygen atoms of 2 other molecules, and its negative oxygen atom can bond to the hydrogen atoms of 2 other molecules. The ideal geometric arrangement for these 4 bonds is a tetrahedron, a shape similar to a 3-sided pyramid. This networking capability is the source of water's unusual properties. In liquid water, the molecules possess enough thermal energy to prevent a stable, ordered network from forming. The hydrogen bonds are transient, constantly breaking and reforming in picoseconds, trillionths of a second. The molecules are in constant motion, and while the network of bonds is persistent, the individual connections are fleeting. This allows the molecules to slide past one another, which is what gives water its fluidity. In this disordered state, the molecules can pack together quite closely. They move into any available gaps and spaces, resulting in a dense arrangement. Their movement prevents them from settling into the ideal, but more open, tetrahedral geometry. This disordered, tightly packed, and dynamic state is what makes liquid water so dense. As the water cools, thermal energy is removed. The molecules move more slowly, and the hydrogen bonds last longer. As the temperature drops below 4 degrees Celsius, small, transient clusters of more orderly, ice-like structures begin to appear. These structures are more open and take up more space. Their increasing presence counteracts the normal effect of cooling, causing the liquid to begin expanding and its density to decrease. 4 degrees Celsius is the balance point where the random packing from thermal motion is at its most compact, just before the ordering effect of the hydrogen bonds begins to dominate. At the freezing point, 0 degrees Celsius, the molecules have so little energy that they can no longer break the hydrogen bonds. They settle into their most energetically favorable configuration, a state where every molecule forms all 4 of its possible hydrogen bonds. To achieve this, the molecules must arrange themselves into a highly ordered, repeating, 3-dimensional pattern known as a crystal lattice. The most common form of ice IH, has a hexagonal crystal structure. In this lattice, every molecule is locked into that ideal tetrahedral arrangement with 4 neighbors. This perfect order, however, comes at a cost in terms of space. To satisfy the geometric requirements of forming 4 straight hydrogen bonds, the molecules are held at a fixed distance from one another, farther apart than their average distance in the chaotic liquid. The structure is rigid and open. The hexagonal rings that form the crystal's backbone are mostly empty space in the middle. The molecules are, on average, farther apart than they were in the jumbled liquid. As the molecules lock into this spacious lattice, the total volume they occupy increases by about 9%. The mass has not changed, but the volume has grown. Since density is mass divided by volume, an increase in volume results in a decrease in density. This is the reason ice floats. It is a direct consequence of the water molecule's polarity and its drive to form a perfect, 4-bonded hydrogen network. In its solid form, the hydrogen bonds win, forcing the molecules into an open, orderly, and less dense crystalline structure. The solid is less dense than the liquid, and so it floats. This single property is one of the crucial pillars supporting life as we know it. In the natural world, as a lake cools in winter, the surface water becomes denser and sinks. This continues until the entire lake reaches a uniform temperature of 4 degrees Celsius, water's point of maximum density. As the surface water cools further, from 4 degrees Celsius to 0 degrees Celsius, it becomes less dense and remains at the surface. When it freezes, the resulting ice is even less dense, so it stays on top. This floating layer of ice then insulates the water below from the cold air above. Throughout the winter, this icy blanket keeps the bulk of the water in a stable, liquid state, often near 4 degrees Celsius at the bottom. This creates a refuge where aquatic life can survive. If ice were denser than water, lakes and rivers would freeze from the bottom up, and this seasonal survival would not be possible. The effect extends to a global scale. The massive floating ice sheets at the Earth's poles reflect a significant amount of solar radiation back into space, helping to regulate the planet's temperature. If ice sank, the darker ocean water would absorb more heat, which would have profound effects on the global climate. The world as we know it is shaped and protected by the fact that solid water floats. From a simple observation, a question emerges that leads to the molecular level. The reason ice floats is not a minor detail. It is a story that begins with a universal rule of physics and reveals water as a significant exception. We found the explanation in the water molecule's bent, polar structure. We saw how this gives rise to a network of hydrogen bonds, which in the liquid state are transient and disordered, allowing for dense packing. In the solid state, these same bonds take over, locking the molecules into a rigid, open, and less dense crystal. This property is not just a scientific curiosity, it is a fundamental feature of our planet. It insulates our waters and helps to regulate our climate. The next time you see ice floating in a glass, it is worth remembering the molecular geometry that makes it possible, and the ways in which that geometry has allowed for life on Earth to exist as it does. Water has many unusual properties that arise from its structure. Beyond its density anomaly, which of its other characteristics do you find most interesting? Its high surface tension, its ability to dissolve many substances, or another property entirely? Let us know in the comments below. Liquid water's organized chaos finally explained. We see it every day. You drop a few ice cubes into a glass of water, and they float. It seems simple, maybe even a little boring. It's one of the first science facts we ever learn. But what if I told you that this simple act is the result of a molecular rebellion? A quirk of physics so strange, so contrary to the laws that govern pretty much everything else, that it literally makes life on Earth possible. For decades, scientists thought they had it all figured out. They pictured liquid water as a chaotic jumble of molecules, just a microscopic mosh pit with no rhyme or reason. But they were wrong. The truth is far more elegant, way more complex, and infinitely more fascinating. What's really happening in your glass is a state of organized chaos. A frantic, high-speed dance where allegiances are formed and broken a trillion times a second. Understanding this hidden structure doesn't just explain why ice floats, it reveals a fundamental secret to our very existence. The story of water isn't a simple one. It's a story of strange physics, broken rules, and a beautiful, microscopic architecture that shapes our entire world. The grand misconception: water, the rule breaker. To really appreciate how bizarre water is, you first have to understand the rules it breaks. In the world of chemistry and physics, there are certain expectations. Predictable behaviors. One of the most basic is what happens when you cool a liquid until it turns into a solid. Think of almost any other substance. Molten iron, for instance. As it cools, its atoms lose energy, slow down, and pack themselves together more and more tightly. The solid form, pig iron, is way denser than its liquid state. If you could toss a chunk of solid iron into a vat of molten iron, it would sink straight to the bottom. Same for wax, for nitrogen, for almost everything. Molecules in a solid are just packed together more neatly and tightly than in a liquid. That's normal. And then there's water. Water is the grand exception. A chemical rebel. When you cool liquid water, it follows the rules at first. It gets denser and denser, just like you'd expect. But then, as it gets close to freezing, something wild happens. At around 4 degrees Celsius, it hits its maximum density and then starts doing the exact opposite. As it gets colder, from 4 degrees down to 0, it actually begins to expand. The molecules start pushing each other away. So when it finally freezes into ice, its solid form is less dense than its liquid form. Specifically, it's about 9% less dense. And that is why ice floats. For the longest time, the scientific model for this was, let's just say, incomplete. The main idea was that liquid water was pure chaos, and ice was an organized, crystalline structure. The floating was explained because, well, that crystal just happened to be less dense. This was correct, but it missed the profound beauty of why. It didn't capture the incredible, dynamic reality of the liquid state. The old model couldn't properly explain all of water's other weird habits, its so-called anomalies. Why does water have such a crazy high boiling point for a molecule of its size? Why can insects walk on its surface? A property we call surface tension, which is higher than almost any other liquid. Why can it absorb so much heat without changing its own temperature? A quality that stabilizes our entire planet's climate. All these questions pointed to something more going on in liquid water than just a random mess. The clues were hiding in plain sight, suggesting that liquid water wasn't pure chaos, but something far more structured and far more mysterious. The simple explanation wasn't enough. The real, aha, moment is in understanding the hidden life of the liquid itself. It turns out, the chaos had an organization all its own. The molecular heart of the matter, a tiny magnet. To get to the bottom of water's secret, we had to zoom in. Way in, down to a single water molecule, hydrogen oxide. It sounds simple, a formula we all learn as kids. Two hydrogen atoms bonded to one oxygen atom. But this simple setup hides an imbalance that is the key to everything. Think of it like a tiny, V-shaped magnet. The oxygen atom is an electron hog. In the bonds it shares with the two hydrogen atoms, the oxygen pulls the shared electrons closer to itself. This is a property called electronegativity. Because the negative electrons spend more time buzzing around the oxygen atom, it develops a slight negative charge. The two hydrogen atoms, having their electrons pulled away, are left with slight positive charges. So now you have a molecule with a negative end, the oxygen, and a positive end, the hydrogens. Scientists call this a polar molecule. It has poles, just like a magnet. This polarity is everything. It's what allows water molecules to talk to each other. When you have a glass of water, you don't just have trillions of hydrogen oxide molecules ignoring one another. Instead, the slightly positive hydrogen end of one molecule is attracted to the slightly negative oxygen end of a neighbor. This attraction is called a hydrogen bond. Now, it's really important to get this. A hydrogen bond is not the same as the strong covalent bonds holding the hydrogen oxide molecule itself together. Those internal bonds are like a superglued handshake, they're incredibly strong. A hydrogen bond, on the other hand, is more like a fleeting, gentle handshake. It's a weak attraction, about 20 times weaker than a covalent bond, but what these bonds lack in strength, they make up for in numbers and their dynamic nature. For a long time, understanding water was all about figuring out what these hydrogen bonds were doing. Early theories from over a century ago imagined liquid water as a mix of different types of molecules, maybe some loners and some small clusters. But it was realizing this huge, interconnected network of hydrogen bonds that really started to unlock the puzzle. Every single weird property of water, its high boiling point, its surface tension, its ability to store heat, and that bizarre density anomaly. All of it comes from these tiny, electrostatic handshakes. To boil water, you don't just have to give the molecules enough energy to fly apart. You have to put in extra energy to break all those hydrogen bonds holding them together. That's why it has a high boiling point. The strong cohesion between molecules at the surface, all holding hands via hydrogen bonds, creates that high surface tension. But the most fascinating part is what these bonds do in the liquid state versus the solid state. They are the directors of the whole molecular ballet. This tiny polarity, this simple fact that a water molecule is like a weak, V-shaped magnet, is the first domino. It sets the stage for the organized chaos of liquid water and the perfect order that lets ice float. The organized chaos, a dance of a trillion handshakes. This is where we throw the old textbook models out the window. The idea of liquid water as a random soup of molecules is a massive oversimplification. The reality is a frantic, beautiful, and highly structured dance. A state of true, organized chaos. In a glass of room temperature water, the molecules are buzzing with energy, sliding past each other, tumbling, and vibrating. But they aren't free. At any given instant, each water molecule is trying to form hydrogen bonds with its neighbors. That polarity we talked about is always there, always pulling them together. But the heat in the system is constantly working to break those bonds apart. The result is an ever-changing network. Hydrogen bonds form, hold for an impossibly short time, and then break, only to reform with a new neighbor moments later. How fast? Research shows these bonds break and reform on the order of a picosecond, that's a trillionth of a second. Imagine a dance where partners switch a trillion times every second. That's the world inside a drop of water. That's the chaos. It's a relentless, high-speed exchange. But here's the organized part. Even in this frantic dance, there's structure. On average, each water molecule is hydrogen bonded to about 3.4 of its neighbors. It's less than the maximum possible 4, but it's a long way from 0. The liquid isn't a free-for-all. It's a highly connected, though temporary, network. Think of it as a crowded dance floor. The old model was just people bouncing off each other. In the organized chaos model, the dancers are constantly trying to hold hands, forming small, fleeting groups. A dancer might hold hands with a few partners for a fraction of a second, then let go and grab another. The picture is one of constant motion, but it's motion governed by the rule of hydrogen bonding. This is the state that's denser than ice. And here's the totally counterintuitive reason why. Because the bonds are constantly breaking and reforming, the molecules have the freedom to move and pack themselves closer together. They can slide past one another and fill in the gaps. The chaos gives them a strange kind of efficiency. They aren't locked into fixed positions. That fleeting nature of their connections allows for a denser arrangement. So, when you look at a glass of water, don't picture a random collection of molecules. Picture a shimmering, dynamic web of connections being woven and unwoven a trillion times per second. Picture a state that is both chaotic in its speed and organized in its relentless attempt to form structure. This organized chaos is the true nature of liquid water. And it's the perfect setup for the grand finale, the act of freezing. The Crystal Palace, from chaos to order. So what happens when we start to cool the water down? The dance begins to change. As the temperature drops, the molecules lose energy. They move more slowly, they vibrate less frantically. The energy that was breaking the hydrogen bonds starts to fade. As the molecules slow, those fleeting hydrogen bond handshakes last longer. A connection that might have lasted a fraction of a picosecond might now last for a few. The dancers are slowing down, holding on to their partners for longer. As water cools from room temperature down to 4 degrees Celsius, this slowing down lets the molecules pack even more closely for a bit, which is why water gets denser. They can still slide past each other, but with less frantic energy, they find tighter packing arrangements. The dance floor gets a little more crowded. But then, below 4 degrees Celsius, the hydrogen bonds really start to take over. The molecules are now moving so slowly that the gentle pull of the hydrogen bonds becomes the main organizing force. They aren't just trying to form bonds, they're succeeding. And they are driven by their V-shape to form a very specific, very beautiful structure. When the freezing point of 0 degrees Celsius is reached, the dance stops. Chaos gives way to perfect, crystalline order. The hydrogen bonds lock into place. Every single water molecule now does something it could never do in the liquid state. It forms 4 stable, strong hydrogen bonds with 4 of its neighbors. Not 3.4, but exactly 4. And they do this in a very specific geometric arrangement, a repeating hexagonal lattice. Imagine trillions of molecules snapping into formation, each one holding hands with 4 neighbors in a perfect tetrahedral configuration. The result is a stunningly open and spacious structure. A crystal palace on a molecular scale. And this is the aha moment. This is the secret. To satisfy the geometric demands of forming 4 perfect hydrogen bonds, each water molecule has to push its neighbors farther away than they were in the chaotic liquid state. The bonds themselves create distance. The crystal lattice is full of empty space, with hexagonal voids woven into its very structure. Think back to our dance floor. In the liquid state, the dancers were weaving between each other, packing the floor tightly. Now, at freezing, the music has stopped, and every dancer has locked arms with four others in a perfectly spaced, choreographed pose. To get into that perfect formation, everyone had to take a step back, creating open space on the dance floor. The total area they take up is now larger. This is why ice is about 9% less dense than liquid water. The organized, rigid structure of ice takes up more volume than the disorganized, chaotic tumble of liquid water. It's a direct result of the hydrogen bonds finally winning their battle against heat. They build their perfect, spacious structure, and that structure floats. The apparent chaos of the liquid was actually a denser, more compact state than the perfect order of the solid. The world that water made. So, ice floats. It seems like a simple fact we take for granted. But the consequences of this one weird property are so profound. It's no exaggeration to say that life as we know it, and the face of our planet, depend on it. Let's imagine a world where water behaved normally, where its solid form was denser than its liquid. What would happen? As winter came, the surface of a lake would cool, get denser, and sink. Warmer water from below would rise, cool, and sink. This convection would continue until the entire lake was at freezing temperature. Then, the first ice crystals would form and, being denser, would sink to the bottom. More ice would form, and it too would sink. The lake would freeze solid from the bottom up. Any fish, plants, or other life would be crushed or frozen. The entire ecosystem would be wiped out every single winter. The oceans would face the same physics. Ice forming in the polar regions would sink to the deep ocean floor, where the sun's rays could never melt it. Over time, the ocean floors would become vast, permanent glaciers. But that's not our world. We live in a world governed by water's beautiful anomaly. In our world, as a lake cools, the same thing happens, but only down to 4 degrees Celsius, water's point of maximum density. Any water that gets colder than that becomes less dense and stays at the top. When it freezes at 0 degrees Celsius, the ice that forms is even less dense, and so it floats. This layer of ice creates a crucial insulating barrier, like a blanket, protecting the liquid water below from the freezing air. Beneath this icy shield, the vast majority of the lake stays liquid, a stable sanctuary where fish and all other aquatic life can survive the winter. This allows for complex, year-round aquatic ecosystems. This principle shapes the whole globe. Life is thought to have started in Earth's oceans, a cradle protected by water's strange and wonderful properties. Even on a smaller scale, this property carves our world. When water seeps into rock cracks and freezes, it expands with immense force, a process called frost wedging that can split giant boulders and break down mountains over time. It all comes back to that organized chaos. It's the dynamic nature of hydrogen bonds in liquid water that lets the molecules pack closely. And it's the final, rigid perfection of those same bonds in ice that forces them apart, creating the buoyant solid that protects life. The fact that ice floats isn't a minor detail. It's a defining feature of Earth. It's a direct result of the microscopic dance we've explored, a dance of polarity, energy, and geometry. The simple act of an ice cube floating in your glass is a quiet testament to a fundamental law of physics being beautifully broken. And it's a reminder that in the strange, rule-breaking behavior of this one substance, the conditions for our own existence were made possible. The story of water is a perfect example of how the simplest questions can lead to the most profound answers. What starts with a floating ice cube ends with a deep dive into molecular physics, our planet's climate, and the very conditions for life. The next time you look at a glass of water, remember the universe of activity inside. A trillion bonds breaking and forming every second in a dance of organized chaos. This frantic ballet is what makes liquid water denser than solid ice, a secret scientists have been unraveling for over a century. Water isn't just a substance. It's a dynamic, structured medium whose quirks have shaped our world in the most fundamental ways. It's a rule breaker, and we owe our existence to its rebellion. If you found this journey into the molecular world as fascinating as we do, consider subscribing and sharing this video. The universe is full of hidden stories like this one. Let us know in the comments what other everyday phenomena you've always wondered about. Water's biggest secret: it expands when it freezes. There is a simple rule in the world of physics, one that seems to govern almost everything. As things get colder, they shrink. We see it when a tight metal lid loosens under cold water. We feel it as the air cools and our bodies huddle inward to conserve heat. Nearly every substance, from the iron in the planet's core to the air itself, follows this rule. When things grow cold, their atoms slow down, vibrate less, and pack together more tightly. They contract. But what if the most common, most essential substance on our planet quietly, and fundamentally, breaks that rule? Perhaps you have forgotten a bottle of water in the freezer. Hours later, you return not to a chilled drink, but to a small scene of household chaos. The bottle is split open, and solid ice has erupted from its core. The mess is a minor inconvenience. But beneath the annoyance is a question. Not how to clean it up, but why it happened. Why did the water, as it grew colder and turned to ice, not shrink like everything else, but expand with enough force to break plastic or even glass? This is not just a strange event in a kitchen freezer. It is a force that shapes the natural world. It is a process that carves mountains, creates fractures in winter roads, and can crack a solid iron engine block left filled with water on a cold night. But here is the most important part of the secret. This strange, rule-breaking behavior, this quiet expansion, is one of the reasons life on Earth is possible. The force that shatters a bottle is the same force that protects lakes, rivers, and oceans from freezing solid each winter. It is a paradox hidden in plain sight. Today, we are going to explore that secret. A journey from the familiar world of floating ice down to the quiet, unseen dance of molecules. A dance that defies a basic law of physics, creates a stunning crystal structure, and in doing so, cradles life itself. To understand how unusual water's behavior is, we first need to understand what is normal. For most substances, there is a direct relationship between temperature and density, a principle known as thermal contraction. As you remove energy, cooling a substance down, its particles lose energy. Imagine a large, open room full of people moving around freely. They are like particles in a liquid state, full of energy, maintaining a certain distance as they move past one another. Now, imagine the energy in the room subsides. The movement slows. People stand closer together, and the space they occupy shrinks. The crowd becomes denser. This is what happens to most materials. When you cool a liquid, like molten wax or iron, its molecules slow their movement. The forces of attraction between them begin to pull them closer. The liquid contracts and becomes denser. When it finally solidifies, the molecules lock into a crystal structure that is almost always more compact than the chaotic arrangement of the liquid state. A piece of solid wax will sink in liquid wax. A piece of solid iron will fall to the bottom of molten iron. This is the rule. The solid is denser than the liquid. Now let's turn our attention to water. For much of its journey, water seems to follow the rules. If you take water at room temperature and begin to cool it, it behaves as expected. The water molecules slow down, they pack closer together, and the water contracts. Its density increases. This continues as you cool it past 20 degrees, past 10 degrees. Everything is normal. But as the temperature nears 4 degrees Celsius, something quietly changes. The contraction stops. At this specific temperature, water reaches its maximum density. It is as compact as it can be in its liquid form. From this point on, as you continue to cool the water from 4 degrees down to its freezing point at 0 degrees Celsius, it begins to do the opposite. Instead of continuing to contract, it starts to expand. The molecules, which had been getting closer, now begin to push each other slightly apart. The volume of the water increases, and so its density begins to decrease. This is known as the anomalous expansion of water. When the water reaches 0 degrees Celsius and begins to change from liquid to solid, this expansion becomes significant. As the liquid locks into the rigid structure of ice, its volume increases by about 9%. A liter of water becomes nearly 1.1 liters of ice. The same number of molecules now takes up more space. This is why ice is less dense than liquid water, and why it floats. The bursting bottle in the freezer is a quiet testament to this 9% expansion. The water inside, with nowhere to go, exerts an immense pressure as it crystallizes, a force strong enough to overcome the container holding it. This behavior sets water apart. It contracts when cooled, but only to a point, before it reverses course and expands into a solid that is less dense than its own liquid. This is not just unusual, it is a fundamental anomaly that asks a deeper question. Why? What is happening at the molecular level to cause water to defy one of the most basic principles of thermodynamics? To find the answer, we have to leave the world we can see and enter the world of the molecule itself. The answer to water's expansion is not found in the liquid as a whole, but in the shape and character of a single water molecule. The formula is simple: H2O. 2 hydrogen atoms bonded to 1 oxygen atom. But the secret is not in the ingredients, it is in the structure. Imagine the oxygen atom as a central sphere. The 2 smaller hydrogen atoms are attached at an angle, giving the molecule a distinct bent shape. The angle is specific, about 104.5 degrees. This geometry is the first critical clue. The second clue is a property called polarity. The bond between oxygen and hydrogen is a covalent bond, meaning they share electrons. But the oxygen atom is highly electronegative. It has a much stronger pull on the shared electrons than the hydrogen atoms do. The electrons, therefore, spend more of their time around the oxygen atom. This uneven sharing creates an imbalance. While the H2O molecule is neutral overall, its charge is not distributed evenly. The oxygen end of the molecule develops a slight negative charge, and the hydrogen ends are left with a slight positive charge. So what we have is a small, bent molecule that is also a tiny magnet. One side is slightly negative, the other slightly positive. This polarity is the key to all of water's unusual properties. It's why it is such a good solvent, why it has such high surface tension, and why a special connection called a hydrogen bond can exist. Understanding polarity is essential. If you hold 2 magnets, you know that opposite poles attract. Now, imagine billions of these tiny molecular magnets in a glass of water. The slightly positive hydrogen end of one molecule will be attracted to the slightly negative oxygen end of a neighbor. This attraction is the hydrogen bond. It is important to distinguish this from the covalent bonds holding a single water molecule together. Those are strong and stable. A hydrogen bond is an intermolecular force, a force between molecules. It is much weaker, about 20 times weaker than a covalent bond. But in a single drop of water, there are billions upon billions of these bonds forming and breaking at any moment. This network of hydrogen bonds defines liquid water. It is a chaotic and dynamic dance. And it is in the changing nature of this dance, from high-energy chaos to a slow, organized pattern, that we will find the answer to why water expands when it freezes. The shape of the molecule creates the dancers, and the hydrogen bonds dictate the steps. Now, we need to see what happens when the energy starts to fade. With an understanding of the polar water molecule and the hydrogen bonds that connect them, we can return to the glass of cooling water with a new perspective. At room temperature, the molecular world is chaotic. The molecules are packed closely, but they are full of thermal energy, causing them to vibrate, rotate, and slide past one another. In this environment, hydrogen bonds are temporary and disorganized. A bond forms for a fraction of a second before the thermal energy breaks it apart, and a new bond forms with a different neighbor. This chaos allows the molecules to pack together quite densely. Now, we begin to cool the water. As we remove heat, we take away kinetic energy. The molecules slow their frantic movement. As they move more slowly, the hydrogen bonds last slightly longer before breaking. The attractions are becoming more significant than the disruptive thermal energy. As we cool from room temperature down to 4 degrees Celsius, two effects are in competition. The first is the normal effect of thermal contraction. Slower molecules pack closer together, which tends to increase density. The second effect, however, is one of ordering. As the molecules slow, the hydrogen bonds start to guide them into more structured, though still temporary, arrangements. Tiny, ice-like clusters begin to form and dissolve within the liquid. These clusters are less dense than the surrounding disorganized liquid. To hold the proper formation, the molecules have to stand a bit further apart. For most of the cooling process, the effect of simple contraction is stronger than the effect of this structural ordering. So, the overall density increases. But at 4 degrees Celsius, there is a quiet balance. The tendency to pack tighter is perfectly offset by the tendency to form these short-lived, space-consuming, ordered clusters. This is why water is at its most dense at 4 degrees Celsius. As we cool the water below *4 degrees Celsius, the balance tips. The effect of structural ordering begins to dominate. As the molecules move even more slowly, these ice-like clusters become more numerous and last longer. The directional hydrogen bonds are now the primary influence. More and more molecules are being forced into these open, pre-ice, arrangements. Because these structures take up more space, the overall volume of the water begins to increase, and its density starts to decrease. This is the anomalous expansion. It is the direct result of hydrogen bonds beginning to win out against the chaos of thermal motion. The water is, in effect, rehearsing the structure of ice while still a liquid. Finally, at 0 degrees Celsius, the thermal energy is so low that the molecules can no longer break free from the hydrogen bonds. The fleeting connections become a permanent, locked grid embrace. The chaotic dance of the liquid ceases, and the molecules snap into their final, rigid positions. This is the moment of freezing. As the last bit of thermal energy leaves at 0 degrees Celsius, the water molecules surrender to the organizing force of their hydrogen bonds. The structure that forms is not a random pile-up, it is a highly ordered, repeating crystalline lattice known as hexagonal ice, the form of nearly all ice and snow on Earth. To be in its most stable state, each water molecule wants to form exactly 4 hydrogen bonds with its neighbors. The 2 positive hydrogens of a central molecule will bond to the negative oxygen of 2 different neighbors. And the negative oxygen of that same central molecule will bond to the positive hydrogens of 2 other neighbors. This creates a perfectly balanced, 4-pointed arrangement around every single molecule, known as a tetrahedral geometry. When billions of these tetrahedral units link together, they form a repeating, interlocking pattern. Viewed from above, this pattern reveals itself as a network of 6-sided rings, hexagons. This is why the crystal is called hexagonal ice, and incidentally, why snowflakes almost always show a 6-fold symmetry. A snowflake is a visible manifestation of this underlying hexagonal lattice. This brings us to the final piece of the explanation: empty space. In the chaos of liquid water, molecules can get very close to each other. But in the rigid structure of the ice crystal, they are held at a fixed distance by the hydrogen bonds. The geometry of the hexagonal rings is surprisingly open. In the center of each of those rings, there is a channel of empty space. The molecules are locked into position on the perimeter and cannot collapse into this central void. This enforced separation is the reason for the expansion. In the liquid state, molecules are, on average, closer together. In the solid state, hydrogen bonds force them into a specific, ordered pattern that is inherently more spacious. The density drops not because the molecules themselves have changed, but because the average spacing between them has increased. And so, the reason becomes clear. Water expands when it freezes because its molecules are polar. This polarity leads to hydrogen bonds. Upon freezing, these bonds lock the molecules into a rigid, open, and spacious hexagonal crystal lattice. The presence of voids within this lattice means that the solid form, ice, is significantly less dense than the liquid form, water. The rule is not just broken, it is overcome by the quiet, inescapable geometry of the H2O molecule. We have traveled deep into the molecular world to understand a bursting water bottle. But this is not just a piece of chemical trivia. This 9% expansion has consequences so profound that it shapes our planet and makes life as we know it possible. The most immediate consequence is that ice floats. Because solid water is less dense than liquid water, when lakes and oceans freeze, the ice forms on the surface. This layer of floating ice creates an insulating blanket between the cold air above and the water below. Ice is a poor conductor of heat, so this surface layer slows the rate of further freezing. Imagine for a moment a world where water behaved normally, where its solid form was denser than its liquid. In such a world, the first ice crystals forming on the surface would sink. More ice would form and sink, and the process would continue until lakes and rivers froze solid from the bottom up. Every winter would erase aquatic life. Our world is different. The floating ice insulates the water below. And the story is made more complete by water's magic temperature of 4 degrees Celsius, its point of maximum density. As a lake cools in autumn, the surface water grows denser and sinks. This continues until the entire lake has reached a uniform 4 degrees Celsius. Only then can the surface cool further, becoming less dense as it approaches 0 degrees Celsius, and staying on top to freeze. This means that beneath the insulating cap of ice, the vast majority of the lake's water remains at a stable 4 degrees Celsius all winter, a hospitable temperature for aquatic life. This anomaly is also a powerful geological force. Water seeps into tiny cracks in rocks. When it freezes, it expands, exerting an incredible pressure from within. This force acts like a wedge, widening the crack. Over seasons of freezing and thawing, this relentless expansion can split boulders and break down mountainsides, slowly turning rock into soil. The ground beneath our feet has been shaped by this molecular expansion. On a global scale, this property helps regulate our planet's climate. The massive ice sheets of Greenland and Antarctica, and the sea ice of the Arctic, are all afloat. Their bright surfaces reflect a significant amount of the sun's energy back into space. This planetary-scale shield helps keep the Earth cool. The simple fact that ice floats rather than sinking to the dark ocean floor is a critical component of our global thermostat. From the survival of a fish in a frozen pond, to the carving of canyons, to the regulation of the planet's temperature, the consequences of water's secret are monumental. It is a life-giving principle woven into the fabric of our world. We began with a simple mystery, a burst bottle in a freezer. An everyday event that holds a clue to one of the most profound secrets of our planet. We have traveled from that visible mess down into the invisible realm of the molecule itself. It begins with the water molecule's bent shape, which makes it a tiny magnet. This polarity allows molecules to connect through hydrogen bonds. In the chaos of liquid water, these bonds are fleeting. But as water cools, that chaos subsides, and the bonds begin to form more ordered, spacious structures. When the final freeze comes, those bonds lock into a rigid crystal palace, a beautiful, open, hexagonal lattice filled with empty space. It is this empty space that causes water to expand, making ice less dense than the liquid it came from. And from that one simple fact, that ice floats, the world as we know it unfolds. Life survives the winter. Mountains are slowly ground into fertile soil. The planet's climate is kept in a delicate balance. The same force that cracks a forgotten bottle is the same force that protects and nurtures our world. So, the next time you drop an ice cube into a drink and watch it float, take a moment. You are not just cooling your beverage. You are witnessing a beautiful molecular dance that has shaped the world. You are watching the silent, powerful operation of water's biggest and most life-giving secret. If this kind of calm exploration into the world helps you unwind, consider liking the video and subscribing to the channel. How one weird fact about water prevents a global ice age. There is a stillness in a glass of water. An ice cube floats, making almost no sound. It is an ordinary moment, easily missed. And yet, within that simple observation lies the reason our world is not a frozen planet. If water behaved like almost everything else, that piece of ice would sink. And in that sinking, a process would have begun long ago that would have left the Earth silent and encased in ice. The fact that it floats is a quiet anomaly. It is a feature of the world so fundamental, we rarely think to question it. But it is the reason life was able to begin and to continue. This is a journey that starts with that single piece of ice. We will look closer into its molecular structure to understand why it is so different. Then we will look out to see how that difference protects a lake through winter and how it keeps the entire planet in a delicate, life-sustaining balance. If this kind of calm exploration helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. The expected order. To understand why water is unusual, it helps to first look at what is usual. For most substances, the physics are simple. As things grow colder, they grow denser. It is a process called thermal contraction. You can see it in a blacksmith's workshop. A piece of metal, taken from the fire, shrinks as it cools on the anvil. Its atoms, once moving with heat, begin to slow. They settle closer together, occupying less space. The same is true for liquids. The mercury in an old thermometer pulls back as the temperature falls. The molecules slow, they draw nearer, and the liquid contracts. This is the predictable way of the material world. When a normal substance freezes, this process reaches its conclusion. Imagine a container of a liquid cooling from the top. The cooler, denser liquid at the surface sinks, pushing warmer liquid up. This continues until, at the surface, the first solid crystals form. These crystals are the coldest and densest state of the substance. And so, they sink. They drift to the bottom, and more liquid is exposed at the surface to freeze and sink in its turn. The container freezes from the bottom up, until it is a solid block. This is the standard behavior for matter. Solids are denser than their liquids. They sink. Understanding this is important, because it shows that water does not just bend this rule. It quietly takes a different path. And in doing so, it makes our world possible. Water's quiet departure. We return to the glass of water. According to the rules that govern most materials, the ice should sink. An iceberg should settle on the ocean floor. But it does not. It floats. This is the first clue that water is following a different set of instructions at the molecular level. The reason is density. When liquid water becomes solid ice, something unexpected happens: it expands. While almost everything else packs tighter, water molecules push each other apart, arranging themselves into a structure that takes up more space. To be precise, its volume increases by about 9%. This makes the solid ice less dense than the liquid water around it. The density of ice is about 0.917 grams per cc, while liquid water is closer to 1 gram per cc. Because it is less dense, it is buoyant. It floats, with most of its mass hidden beneath the surface. This single fact is the anomaly. It is the quiet detail on which everything else rests. There are other substances that expand when they freeze, but water is the only common compound that does this, and the one on which life depends. The force of this expansion is subtle, but strong. A forgotten bottle of water in a freezer can split glass. Over geologic time, this same process weathers mountains, as water seeps into cracks, freezes, and pushes rock apart. But the question is not just what it does, but why. What is happening at the invisible scale of molecules that causes water to arrange itself in this spacious, open way when it freezes? To find the answer, we have to look deeper, into the geometry of the molecule itself, where a special kind of connection changes everything. The molecular architecture. To understand why ice floats, we have to understand the water molecule. It is a journey into the architecture of the very small, and it begins with a shape. The water molecule, H2O, is made of 2 hydrogen atoms and 1 oxygen atom. But they are not arranged in a straight line. Instead, they form a V shape, with the larger oxygen atom at the point and the 2 smaller hydrogen atoms offset at an angle. This shape is the first piece of the puzzle. The second is a property called polarity. The large oxygen atom has a stronger pull on the shared electrons, drawing them closer. This gives the oxygen side of the molecule a slight negative charge, leaving the hydrogen side with a slight positive charge. The molecule is not neutral across its surface. It is like a tiny magnet with a positive and negative end. Now, imagine a drop of liquid water, filled with trillions of these tiny molecular magnets. Opposites attract. The positive hydrogen end of one molecule is drawn to the negative oxygen end of another. This quiet attraction is called a hydrogen bond. In liquid water, the molecules have enough energy to move freely, tumbling and sliding past one another. In this state, hydrogen bonds are constantly forming and breaking, lasting only for fractions of a second. The molecules are packed closely, but without a clear order, like a disorganized crowd. This disordered arrangement gives liquid water its density. As we cool the water, it first behaves as expected. The molecules slow down, and they pack a little closer. But then, as the water approaches 4 degrees Celsius, something unusual happens. It reaches its maximum density. If you cool it further, from 4 degrees Celsius down to 0 degrees Celsius, it begins to expand. It becomes less dense. This happens because as the molecules slow, the hydrogen bonds start to last longer. They begin to guide the molecules into more structured arrangements. These structures are more open and take up more space than the chaotic jumble of warmer water. This organizing influence of the hydrogen bonds starts to overpower the normal tendency to contract. When the temperature finally reaches 0 degrees Celsius, the molecules have lost enough energy that the hydrogen bonds lock into place. They form a highly ordered, 3-dimensional structure, a hexagonal crystal lattice. Each water molecule forms stable hydrogen bonds with 4 of its neighbors, creating a repeating pattern of 6-sided rings. This crystalline structure is what gives most snowflakes their 6 sides. But most importantly, it is very spacious. To achieve this stable, low-energy arrangement, the molecules must hold each other at a fixed distance. The structure is filled with empty channels and voids. It is the order itself that creates the space. So, when water freezes, the same number of molecules now occupy a larger volume. This means a lower density. Ice floats because its frozen, crystalline form is a spacious, open lattice, a shape determined by the polarity of its molecules and the quiet influence of their hydrogen bonds. The lake's winter survival. We now understand the molecular reason for water's strange behavior. But what does it mean for the world around us? To answer that, we can scale up, from the molecule to a frozen lake. The survival of nearly all life in freshwater lakes in cold climates depends on this one fact. In late summer, a deep lake is often layered. The top is warm and less dense, while the bottom is cold and dense. As autumn arrives, the air cools the surface water. This cooler water, down to 4 degrees Celsius, becomes denser and sinks. This sinking pushes warmer water up, which then cools and sinks in turn. This process, called the autumn turnover, mixes the entire lake, distributing oxygen and nutrients from top to bottom. It continues until the whole lake reaches a uniform temperature of 4 degrees Celsius, its point of maximum density. Now, the stage is set. The air temperature drops below freezing. It begins to cool the surface of the 4 degrees Celsius lake. But this time, as the water cools from 4 degrees Celsius towards 0 degrees Celsius, it becomes less dense. It grows lighter. Because it is lighter, it does not sink. It stays on top, forming a cold layer at the surface. Eventually, this layer reaches 0 degrees Celsius and begins to freeze. And because solid ice is even less dense, it floats. The lake freezes from the top down. This sheet of ice is more than just a lid, it is a protective blanket. Ice is a poor conductor of heat, a good insulator. It separates the cold winter air from the liquid water below. No matter how cold the air becomes, the ice slows the escape of heat from the lake. Snowfall adds another layer of insulation, trapping air and slowing heat loss even more. Because of this, most lakes of significant depth never freeze solid. Just beneath the ice, the water might be near 0 degrees Celsius, but deeper down, much of the lake remains at a stable 4 degrees Celsius. The lake becomes a winter refuge, an insulated sanctuary for the life within. Beneath this frozen ceiling, a hidden world continues. Fish, being cold-blooded, slow down. Their metabolism and heart rate drop as they conserve energy. Some retreat to the deepest, most stable water at the bottom. Others, like trout, remain more active just below the ice. Turtles and frogs burrow into the soft mud, their bodies entering a state of near hibernation. Microscopic life waits in the sediment for the spring thaw. All of this, the survival of every fish, every frog, every plant in that lake, is possible for one reason. The ice floated. It created an insulated haven, not a frozen tomb. The global thermostat. The insulating blanket of ice is a brilliant solution for life in a frozen pond, but the implications of this one fact scale up even further, to the level of the entire planet. The same property acts as a global thermostat, preventing a chain reaction that could have plunged the world into a permanent ice age. To understand this, we can perform a thought experiment. We can imagine a world where water is normal, a world where ice is denser than water and sinks. On this alternate Earth, as the first winter approaches, the surface of the oceans and lakes begins to freeze. But here, the ice crystals are denser than the water, and so they sink. A slow, silent drift of ice begins, settling on the bottom. At the surface, new water is exposed to the cold air, which then freezes and sinks. The oceans and lakes begin to freeze from the bottom up. When summer arrives, the sun's rays warm the surface of the water, but they cannot reach the deep, sunken ice. That ice, insulated by the water above it, would not melt. With each passing year, the cycle would repeat. More ice would form and sink, adding to the growing layer at the bottom of the world's oceans. The planet's vast reservoirs of water would become locked away in immense, subterranean glaciers. This would trigger a feedback loop called the ice albedo effect. Bright surfaces, like ice, reflect more sunlight back into space than dark surfaces, like open water. As more of the planet's surface effectively became ice-covered, the planet would absorb less heat. A colder planet would lead to more ice, which would lead to more reflection, which would lead to an even colder planet. There would be no escape. The world would be trapped in a permanent, runaway ice age. Now, we return to our world. Here, floating ice is the circuit breaker that prevents this loop. The vast, floating ice sheets at the poles act as giant reflective shields, bouncing solar energy back into space and helping to regulate the planet's temperature. But because this ice floats, it also insulates the deep oceans from the cold polar air, preventing them from freezing solid. The seasonal cycle of this floating ice is also an engine for global ocean circulation. When sea ice forms, it pushes salt out, creating colder, saltier, denser water. This dense water sinks and drives the deep ocean currents that transport heat around the globe, shaping our climates. And because our ice floats, it is exposed to the sun and warmer air. It melts in the summer, preventing the permanent, year-over-year buildup that would trigger a runaway freeze. Our planet has a reset button that is pressed each spring. The simple fact that ice floats allows the Earth to maintain a delicate thermal balance. It separates a living, blue planet from a static, frozen one. Conclusion: we began with a simple observation, an ice cube floating in a glass. That quiet detail took us on a journey. We looked into the molecular world and saw how the shape of the water molecule and the hydrogen bonds between them force ice into a spacious, crystalline structure, making it less dense than the liquid it forms from. We scaled up and saw how this property allows a layer of floating ice to insulate a lake, creating a sanctuary for life to endure the winter. And finally, we scaled up to the planet. We saw how floating ice acts as a global thermostat, preventing a runaway freeze that would have left the Earth a solid ball of ice. From the smallest molecular interaction to the largest planetary system, the story is the same. The quiet strangeness of water is the key to our world's survival. So the next time you see an ice cube in a glass, take a moment. Watch it bob at the surface. And remember that you are witnessing the principle that keeps our world a living planet. You are looking at the weird fact that saved the world. If this journey from the molecule to the planet has given you a new perspective, let us know in the comments. We read them all, and your curiosity helps shape our next explorations. This kind of research and storytelling is made possible by viewers like you. If you enjoy making sense of the universe, one quiet story at a time, please consider subscribing to the channel. It's the best way to be sure you don't miss our next video. Thank you for joining us. And as always, thanks for watching. How this hidden rule of water saves the world every winter. Every winter, something quiet happens in lakes and rivers across the globe. We see it as a normal part of the season. A serene, frozen surface, perhaps dusted with snow, a picture of stillness. We skate on it, fish through it, and walk across it. But this familiar scene is, from a scientific perspective, deeply strange. The sheet of ice floating on a lake is a protective raft for an entire world beneath. And it only exists because water breaks a fundamental rule that nearly every other substance in the universe follows. What if water behaved like almost every other liquid? What if it followed the simple, logical rules of cooling? The scene would be entirely different. Instead of a floating layer of ice, the cold would settle at the bottom. The depths would freeze first, a solid block growing upward, quietly consuming the water column. The lake would become a tomb, not a sanctuary. A silent catastrophe would unfold every year, erasing countless ecosystems. The reason it doesn't all comes down to a hidden, counterintuitive property of water that makes life, as we know it, possible. This is the story of how a tiny quirk at the molecular level prevents a planetary disaster, season after season. To appreciate how unusual water is, we first have to understand what normal looks like. Let's consider almost any other substance. Imagine a container of liquid wax. As it cools, its molecules lose energy. They slow their frantic, chaotic dance. As they slow, they get closer together. Think of a moving crowd. As people lose energy, they pack in tighter, taking up less space. This is the general rule of thermal contraction. For most substances, cooling means contracting. As the liquid wax cools, the coldest parts become the densest parts. Density is simply a measure of how much mass is packed into a given volume. The more tightly packed the molecules, the denser the substance. So, in our container of cooling wax, the coldest, densest material will naturally sink. The freezing process would begin at the bottom and slowly work its way to the surface. If you were to freeze a block of olive oil, liquid nitrogen, or molten iron, you would find that the solid form is denser than its liquid form. A solid cube of frozen olive oil dropped into liquid olive oil will sink. This is the normal, expected behavior. Solids are denser than their liquids. Now, let's apply this normal rule to a lake. Imagine a lake in late autumn as the air temperature drops, chilling the surface. If water behaved normally, this colder, denser surface water would sink. The warmer, less dense water from below would rise, get chilled, and then it too would sink. This process, called convection, would efficiently cool the entire body of water from top to bottom. Eventually, the water at the bottom would reach its freezing point, 0 degrees Celsius. It would turn to ice. Because this normal ice is denser than the water above it, it would stay at the bottom. The freezing would continue from the lake bed upwards. The layer of ice would grow thicker, a quiet front of solid ice rising toward the surface. Any fish, any hibernating turtle, any dragonfly nymph in the mud would be trapped. As the ice advanced, their world would shrink until it vanished, encasing them in a frozen tomb. By midwinter, the entire lake could be a solid block of ice. And because water holds heat so well, a lake frozen solid might not fully thaw the following summer, leading to an accumulation of ice year after year. Life in that lake would be impossible. If water followed the same rules as everything else, our planet's freshwater ecosystems would be barren blocks of ice for much of the year. This is the outcome that is averted, all thanks to water's quiet refusal to follow the rules. This is where the story takes a turn into the strange. Water does not follow the rules completely. As you cool liquid water from room temperature, it does, at first, behave as expected. It contracts and becomes denser. The molecules slow down, they pack a little closer, and the colder water sinks. This continues as the whole lake cools. But then, something subtle happens. The temperature drops past 10 degrees, past 8, past 5, and then it reaches 4 degrees Celsius. At this precise temperature, water achieves its peak density. It is at its heaviest, most compact state, not as a solid, but as a liquid. This is the turning point. This is the hidden rule. If you continue to cool the water below 4 degrees Celsius, a counterintuitive process begins. Instead of continuing to contract, the water starts to expand. It becomes less dense. Water at 3 degrees is lighter than water at 4 degrees. Water at 2 degrees is lighter still. This is backward compared to almost every other substance. It's as if our cooling crowd, upon getting even more tired, decided to all take a step away from each other, creating more space between them. So, let's return to our lake in autumn. The air is cold. The surface water cools, becomes denser, and sinks. This cycle, known as fall turnover, continues, mixing the water until the entire lake, from top to bottom, reaches that quiet temperature of 4 degrees Celsius. At this point, the whole body of water is at its maximum possible density. Now, the air gets even colder, pushing the temperature of the surface below 4 degrees. This time, something different happens. This layer of 3-degree water is now less dense than the 4-degree water below it. So, it doesn't sink. It floats. The 2-degree water that forms on top of that is lighter still, and it also floats. The lake has now stratified. At the bottom is a vast, stable reservoir of the densest water possible. A liquid sanctuary at 4 degrees Celsius. Above it are progressively colder, lighter layers. At the very top, exposed to the freezing air, is the coldest, least dense water of all. When the surface finally reaches 0 degrees Celsius, it begins to freeze. As it solidifies, it dramatically expands. The molecules arrange themselves into a wide-open crystalline structure. In fact, ice is a full 9% less dense than the cold liquid water it forms from. And because it is so much less dense, it floats. A solid sheet of ice forms on the surface, covering the liquid water below. The doomsday scenario of the lake freezing from the bottom up has been completely averted. Instead of a solid tomb, the lake now has a protective ceiling. But to understand why this happens, we have to look at the molecules themselves, and the invisible force that governs their quiet, orderly dance. The secret to water's life-saving anomaly lies in its shape. Let's picture a single hydrogen oxide molecule. It has one large oxygen atom and two smaller hydrogen atoms, arranged not in a straight line, but in a bent, V-shape. This shape is crucial. Within the molecule, the atoms share electrons, but not equally. The large oxygen atom has a stronger pull, drawing the shared electrons closer to it. This gives the oxygen atom a slight negative charge and leaves the two hydrogen atoms with slight positive charges. This makes the water molecule polar. It has a negative end and a positive end, like a tiny, weak magnet. Now, imagine billions of these tiny magnets tumbling in liquid water. The positive end of one molecule is attracted to the negative end of another. This specific attraction, between a hydrogen on one molecule and an oxygen on another, is called a hydrogen bond. It is not as strong as the bonds holding the molecule itself together, but it is significant. You can think of it as molecules briefly holding hands with their neighbors before letting go and grabbing another. In liquid water, the molecules have a lot of energy. They zip and tumble constantly. The hydrogen bonds are in a state of flux, forming and breaking in quadrillionths of a second. This constant motion keeps them relatively close, but in a disorganized, fluid jumble. As the water cools, the molecules slow down. The hydrogen bonds become a little more stable, and the molecules pull in closer, making the water denser. This is the normal behavior we see down to 4 degrees Celsius. But as the water cools below *4 degrees, the hydrogen bonds begin to assert themselves in a new way. As molecules slow even more, they have time to find their ideal, lowest energy arrangement. And for water, that ideal arrangement is not to pack as tightly as possible. Instead, it's to form a highly ordered crystal lattice, where every molecule forms 4 strong hydrogen bonds with its neighbors. To achieve this perfectly ordered structure, the molecules have to be pushed farther apart than they were in their chaotic liquid state. The geometry of the hydrogen bond dictates a specific angle and distance. The resulting structure is a hexagonal lattice that is surprisingly open, full of empty space. Think of neatly stacking organized boxes versus throwing them in a messy pile. The messy pile might take up less space. The perfectly ordered arrangement creates empty channels between the stacks. This crystalline structure is what we call ice. When water freezes, its molecules lock into this rigid, spacious lattice. Because the molecules are now held at a greater average distance, the same number of molecules takes up more volume. More volume for the same mass means lower density. This is why ice is about 9% less dense than liquid water, and it is why it floats. The 4-degree mark is the precise balance point. As water cools from high temperatures, thermal contraction dominates, slower molecules pack tighter. But below 4 degrees, the structural effect of hydrogen bonding begins to dominate. The molecules start arranging themselves into more open, pre-ice clusters, causing the structure to expand. At 4 degrees Celsius, water is at that perfect point of being cold and slow, but not yet so dominated by the rigid lattice. It is the densest it can be. This delicate balance is the engine of the life-saving process that unfolds every winter. Now we can return to our lake with a new understanding. It is late autumn. The surface of the lake cools and sinks, displacing the warmer water from the depths, which rises to be cooled in turn. This elegant, powerful dance is the fall turnover. It is the lake taking a deep breath before winter, mixing nutrients and oxygen throughout the ecosystem. This continues until the entire lake reaches a uniform 4 degrees Celsius. It is now primed for winter. Then, a cold front arrives. The surface water cools below 4 degrees Celsius. But now, the hidden rule takes over. The layer of 3 degrees Celsius water is less dense, so it stays on top. As it cools to 2 degrees Celsius, it becomes less dense still. A stratification is established, with the coldest water on top and the warmest, heaviest water sitting safely at the bottom. Finally, the surface reaches 0 degrees Celsius and ice begins to form. And because this solid ice is significantly less dense, it floats. A skim of ice appears, then thickens, forming a solid cap across the lake. This sheet of ice is more than just a frozen layer, it is an insulator. Ice, especially with snow on top, is a remarkably poor conductor of heat. This floating shield now dramatically slows the rate at which the rest of the lake can lose heat to the frigid air. It protects the liquid world below. And in that world below the ice, life goes on. Down in the dark, silent depths, the water remains at a stable, life-sustaining 4 degrees Celsius. This is the sanctuary. Fish, being cold-blooded, have their metabolism slow way down. They survive the long winter in this protected environment. Frogs and turtles burrow into the mud where the ice will never reach them, their heartbeats slowing to a near standstill. Insect larvae wait patiently in the sediment. The entire ecosystem is in a state of suspended animation, protected by this quiet rule of water. Without this floating, insulating layer, the relentless cold would pull heat from the lake until it froze solid from the bottom up. Every year would be a mass extinction event for freshwater life across huge parts of our planet. The implications ripple outwards. In the spring, the process reverses, initiating the spring turnover that again redistributes nutrients and oxygen, kicking the ecosystem back into high gear. The same principle applies to oceans. Sea ice floating in the polar regions helps regulate the Earth's climate. Its bright surface reflects sunlight back into space, keeping the planet cooler. This single, strange property of water, that its solid form floats on its liquid form, is a cornerstone of our planet's climate system and a fundamental requirement for life as we know it. If this kind of calm exploration into the hidden world of physics helps you see things a little differently, consider liking the video and subscribing to the channel. And wherever you are right now, whether near a frozen lake or somewhere warm, feel free to share where you're watching or listening from. The next time you see a frozen lake, see more than a sheet of ice. See a shield. See an insulating blanket protecting a hidden world. In a universe where almost every substance becomes heavier when it freezes, water took a different path. It chose to expand, to become lighter, to float. This isn't a small quirk. It is a fundamental, life-giving property of our planet. This hidden rule of water prevents a global catastrophe every single winter. It creates a sanctuary in the depths, allowing life to weather the cold and re-emerge in the spring. It is a quiet, elegant reminder that we live on a planet governed by exquisitely fine-tuned laws, and our existence depends on the beautiful and baffling strangeness of water. What if ice sank? Imagine a world where our oceans, the cradle of life, were quietly remade. A world where a runaway cooling was not a distant threat, but a simple consequence of water behaving like almost every other liquid on the planet. This isn't a story of fiction. It would be our reality if not for a single, subtle difference. When you drop an ice cube into a glass of water, it bobs on the surface. It's a mundane observation, something we see and take for granted. But in that simple act of floating, a profound and life-sustaining principle is at work. Water, in its solid form, is less dense than its liquid form. This is a strange, almost quiet rebellion against the normal rules of physics, where solids are almost always denser than their liquid counterparts. But what if it wasn't? What if water followed the rules? What if, when the temperature dropped, the ice that formed on the surface of our lakes, rivers, and oceans was heavier than the water around it? What if ice sank? This single, seemingly small change would not just alter our world, it would unmake it. It would set in motion a chain reaction, freezing our planet from the bottom up, erasing nearly all life in the seas, and leaving behind a world that might never recover. The story of our planet, of life itself, is tied to this one strange property of water. And to understand the world we have, we must first journey to the world that would exist if ice behaved like anything else. A world where the oceans slowly become solid, where the climate unravels, and where the course of history is born from the bottom of the sea. So, what if ice sank? The answer is stark and unforgiving. The intricate web of life, the stable climate we depend on, and the very history of our planet would be rewritten. Let's follow this thread, and watch a familiar world come undone. A world freezing from the bottom up. In our world, winter arrives gently at a lake's edge. The air cools, the surface water chills, and a thin sheet of ice forms, floating on top. This layer of ice acts as a protective blanket, an insulating shield that protects the liquid water below from the freezing air above. Under this cover, life goes on. Fish swim, plants wait for spring, and the ecosystem survives. But in a world where ice sinks, the arrival of winter is a quiet sentence. The moment the first ice crystal forms on the surface of a polar sea or a northern lake, it doesn't float. It's denser, heavier than the water around it, and so it begins to fall. Like a steady, silent snowfall, these ice crystals would drift down through the water column, settling on the bottom. The surface, now stripped of its ice, is once again exposed to the frigid air. It freezes, and this new layer of ice also sinks. And so the process repeats. This isn't a slow, seasonal freezing. It's a quiet, runaway reaction. A relentless cascade of sinking ice that begins to fill our oceans from the seabed up. The polar regions would be the first to change. In the Arctic and Antarctic, where ocean temperatures are already close to freezing, the effect would be immediate. During the long polar winters, the surface of the ocean would constantly freeze and shed its ice into the depths. Layer upon layer would accumulate on the ocean floor, forming a growing, permanent glacier in the abyss. The heat that would normally be trapped in the ocean by a floating ice cap would escape, accelerating the cooling. Imagine the deepest parts of the ocean, the trenches and abyssal plains, slowly being filled with a creeping, crystalline solid. Under the immense pressure of these depths, the sunken ice would be compacted into dense, unfamiliar forms, perhaps miles thick, that might never melt again. These deep ocean glaciers would become permanent fixtures of the planet, quietly locking away vast quantities of Earth's water into an eternal, solid state. This process wouldn't be confined to the poles. Ocean currents, the planet's great circulatory system, would carry cold, dense water from the polar regions towards the equator. As this super-chilled water moved through temperate zones, it would cool the surface from below, making it easier for ice to form even in once milder climates. Lakes and seas that used to experience only partial freezing would now begin to solidify from the bottom up. Think of the Great Lakes in North America or the vast lakes of Siberia. In our world, they develop an ice cap that allows life to persist below. In this alternate reality, they would become solid blocks of ice. Any life within them would be crushed or frozen. The spring thaw would become a distant memory, with the ice accumulating at the bottom, insulated from the sun's warmth by the water above. It would take far longer to melt, if it melted at all. Entire freshwater ecosystems would be sterilized, year after year. The oceans would follow. Within decades, perhaps, the relentless cycle of surface freezing and sinking ice would turn the majority of the world's oceans into solid, lifeless blocks. Only a shallow, briny, and frigid layer of liquid might remain at the surface in the tropics, a remnant of a once vibrant global ocean. The world's water would be trapped, the planet's pulse would slow, and the stage would be set for an even greater change: the silencing of the seas. The silencing of the seas. The oceans are not just bodies of water. They are the planet's primary life support system. They generate more than half of the oxygen we breathe, anchor the global food web, and regulate our climate. The freezing of the oceans from the bottom up would not just disrupt this system. It would systematically dismantle it, piece by piece, leading to a mass extinction that would reshape Earth's history. The change begins at the very bottom of the food chain, with the most important organisms you may have never seen, phytoplankton. These microscopic organisms float in the sunlit upper layer of the ocean. Through photosynthesis, they convert sunlight into energy, forming the base of the entire marine food web. They are the grass of the sea, and everything, from the smallest shrimp to the largest whale, depends on them. In a world of sinking ice, their existence becomes impossible. The constant freezing would create an ever-thickening slush and, eventually, a solid lid of ice over vast stretches of the ocean. This surface would block the sunlight. Without light, photosynthesis stops. The phytoplankton would be the first to fade, starving in the sudden darkness. Their demise would be swift and total. And when they vanish, they take the planet's oxygen with them. Scientists estimate that phytoplankton produce between 50 and 80% of the oxygen in our atmosphere. Their collapse would mean a catastrophic drop in global oxygen levels, creating a crisis for all air-breathing life. With the primary producers gone, the food web collapses in a quiet domino effect. The tiny zooplankton that graze on phytoplankton would vanish next. Then comes the krill, the small crustaceans that feed trillions of fish, birds, and even the great baleen whales. With their food source gone, the krill populations would crash, and the oceans would fall silent. The subsequent disappearances would be hard to imagine. Schools of herring, sardines, and anchovies would fade away. The cod, tuna, and mackerel that prey on them would starve in their turn. The global fishing industry, a source of protein for over 3 billion people, would simply cease to exist. Marine mammals would face a particularly grim reality. Whales, dolphins, and seals would find their food sources gone. Species that rely on sea ice in our world, like walruses and polar bears, would find their hunting grounds have vanished, replaced by either open, churning water or a solid, impenetrable sheet of ice. Their extinction would be rapid and inevitable. Even the creatures of the deep would not be spared. They depend on marine snow, a constant shower of organic material from the upper layers of the ocean. With the surface world sterilized, this vital flow of nutrients would cease. The abyssal plains would become barren deserts. The only life that might survive would be the extremophiles clustered around hydrothermal vents on the ocean floor. These ecosystems derive their energy not from the sun, but from chemicals spewing from the Earth's crust. They would be encased in a planet-spanning tomb of ice, isolated pockets of life in an otherwise dead ocean. The shorelines would become graveyards. The tides would wash up billions of dead and dying creatures, a rotting testament to the collapse of an entire biosphere. The oceans, once the cradle of life, would have become a frozen, sterile monument to a simple change in physical law. And the consequences of this great dying would not be contained to the sea. They would spill onto the land, quietly beginning the collapse of human civilization. A world disconnected. The freezing of the oceans would not be a distant, isolated event. It would be a planetary shockwave that would unravel the foundations of modern human civilization. Our global society is woven into the fabric of the marine world, and its sudden unraveling would trigger a quiet cascade of failures in our economic, political, and social systems. The first and most immediate impact would be the end of global trade. Our modern economy is built on maritime shipping. Over 80% of global trade by volume is carried by sea, including oil, gas, grain, and manufactured goods. In a world where ice sinks, the great shipping lanes of the world would become impassable. Imagine the North Atlantic choked with a grinding slurry of sinking ice and eventually freezing over. The same would happen to the Pacific, the Indian Ocean, and every other major waterway. Tankers carrying oil would be frozen in place. Container ships laden with goods would be locked in ice. Grain shipments that feed entire nations would never reach their destinations. The global supply chain would not just be disrupted, it would be severed. The effect on the economy would be instantaneous. Industries dependent on imported materials would shut down. Shelves in stores would go bare. The interconnected global economy, the engine of modern prosperity, would simply cease to function. Alongside this economic collapse would come a devastating food crisis. The collapse of marine ecosystems would wipe out the fishing industry. But the impact on food would extend far beyond fish. The drastic changes in the ocean would have a profound effect on the world's climate, disrupting agriculture on land. The freezing oceans would no longer regulate planetary temperatures, leading to wild, unpredictable swings in weather. Monsoons could fail. Regions that were once fertile could be plunged into drought, while others could experience unprecedented floods or blizzards. Global crop failures would become the norm. Faced with economic collapse and widespread famine, societies would begin to break down. Social unrest would erupt. Nations would turn inward, hoarding resources. International cooperation would evaporate, replaced by suspicion and hostility. Conflict would be inevitable. Scarcity is the mother of war, and in this new world, everything would be scarce. Wars could break out over access to the last remaining unfrozen rivers or arable land. They would be brutal, primitive struggles for survival. As governments lose control, central authority would disintegrate. Humanity would be thrown back into a new dark age, but with a crucial difference. The environment itself would be actively hostile. The planet would be descending into a new ice age, and survival would mean a constant battle against the encroaching cold. The secret of the hydrogen bond. This vision of a frozen Earth is the world we would inhabit if ice obeyed the simple rules that govern almost every other substance. But it doesn't. Our world was saved from this fate by a peculiar property of water, rooted in its very molecular structure. The savior of our planet is an invisible force known as the hydrogen bond. To understand why ice floats, we have to zoom in to the level of individual water molecules. A water molecule, H2O, is simple. One oxygen atom and two hydrogen atoms. But its shape is what makes it special. The hydrogen atoms are attached at an angle, forming a V-shape, like a tiny boomerang. The oxygen atom pulls the tiny electrons from the hydrogen atoms closer to itself. This gives the oxygen end of the molecule a slight negative charge, and the hydrogen ends a slight positive charge. This property is called polarity. Water molecules are like tiny, weak magnets. In liquid water, these molecules are constantly moving and sliding past one another. The positive hydrogen end of one molecule is attracted to the negative oxygen end of another. This attraction is a hydrogen bond. In liquid form, these bonds are fleeting, allowing the molecules to pack together closely. As liquid water cools, the molecules slow down, and they pack even tighter, causing the water to become denser. This is normal behavior. But for water, something strange happens at 4 degrees Celsius. Below this temperature, as it gets colder, it starts to expand. It becomes less dense. When the temperature finally reaches 0 degrees Celsius, this process locks into place. The hydrogen bonds are no longer fleeting. They organize the water molecules into a rigid, ordered, three-dimensional structure, a crystal lattice. And it is the specific shape of this crystal that saves the world. The molecules arrange themselves in a hexagonal or six-sided pattern. This structure is strong, but it is also remarkably open. The molecules are held further apart in this rigid crystal than they were when they were jumbling around as a liquid. Think of it like a crowded dance floor. When the music is fast, people are packed tightly together. This is liquid water. But when the music slows for a formal dance, everyone pairs up and moves into a structured formation, leaving more empty space between them. This is ice. Because the molecules in ice take up more space, ice is less dense than liquid water, about 9% less dense. And because of this lower density, it floats. An object in a fluid is pushed up by a force equal to the weight of the fluid it displaces. Since a block of ice weighs less than the volume of water it displaces, the buoyant force wins and the ice rises. This single, elegant consequence of the hydrogen bond is the barrier that stands between us and the frozen world. It ensures that lakes and oceans freeze from the top down. It provides the insulating blanket that protects aquatic life. It preserves the liquid oceans that regulate our climate and harbor the majority of life on Earth. It is a quiet, molecular property that happens billions of times a second, and it is the single most important reason our planet is a vibrant, living world and not a dead ball of ice. A planet shaped by floating ice. Because ice floats, our world is a place of liquid oceans, dynamic climates, and abundant life. This one peculiar property of water has shaped every aspect of our planet. The most direct benefit is insulation. The layer of ice that forms on top of a lake or a polar sea is a powerful insulator. Just as a blanket traps your body heat, this sheet of ice separates the liquid water below from the frigid air above. Temperatures in the Arctic winter can plummet to -40 degrees Celsius, but just a few feet below the ice, the water remains stable, just above freezing. This insulation is the key to survival for almost all aquatic life in cold climates. Fish, amphibians, and countless other organisms can live through the winter in the liquid refuge beneath the ice. Without this floating shield, these bodies of water would freeze solid, and life within them would be extinguished every year. Floating ice also plays a monumental role in regulating the Earth's climate through a process known as the ice albedo feedback. Albedo is a measure of how reflective a surface is. Ice is bright white and reflects a large portion of the sun's radiation back into space. Darker surfaces, like open ocean water, absorb more of the sun's energy. The vast ice sheets at our poles act like giant mirrors, reflecting solar energy and helping to keep the planet cool. This creates a self-regulating feedback loop that is a major driver of Earth's ice ages and interglacial periods. In the world where ice sinks, the dark, energy-absorbing ocean surface would remain exposed, creating a very different and more unstable climate dynamic. The existence of liquid oceans, made possible by floating ice, allows them to function as the Earth's great heat engine. Ocean currents transport enormous amounts of heat from the tropics toward the poles, moderating the climate of places like northern Europe. In the world of sinking ice, these vital currents would grind to a halt entirely, creating a climate of violent extremes. Furthermore, the oceans absorb a huge amount of carbon dioxide from the atmosphere, a service vital for keeping the greenhouse effect in check. A frozen ocean could not perform this function. The very existence of complex life on Earth is arguably a consequence of floating ice. Life is thought to have begun in the oceans. The stability provided by vast, liquid oceans over billions of years allowed for the slow, methodical process of evolution to unfold. A planet whose oceans were prone to freezing solid would have been a far more difficult environment for life to gain a foothold, let alone flourish into the biodiversity we see today. Every time you see a picture of an iceberg, a frozen lake, or even just the ice cubes in your drink, you're looking at a symbol of our planet's profound luck. You are seeing the physical manifestation of a molecular quirk that prevented a global apocalypse and allowed our living world to exist. The delicate balance of our planet is truly astounding, and it's built on principles that are both strange and beautiful. If this kind of calm exploration into the world helps you unwind, consider liking the video and subscribing to the channel. And for another look at how planetary systems can go catastrophically wrong, you might enjoy our video on, what if the Earth stopped spinning? The thought experiment of sinking ice does more than just paint a picture of a different Earth. It serves as a quiet reminder of the intricate nature of the world we live in. Our planet is a dynamic, interconnected system, where the smallest details at the molecular level can have consequences on a global scale. The hydrogen bond, the V-shape of a water molecule, the resulting 9% difference in density between ice and water. These are not just trivial facts. They are the pillars upon which our entire biosphere rests. They are the silent guardians that prevented a runaway freezing event that would have sterilized the planet. This story also carries a quiet echo for our time. We are living through an era where another property of ice, its melting point, is being tested. The massive ice sheets of Greenland and Antarctica are melting at an accelerating rate. This influx of fresh water into the oceans is altering water density and threatening to disrupt the very ocean currents that keep our climate stable. The potential consequences are a faint but clear reminder of the delicate balances we explored in our hypothetical world. We were saved from the nightmare of sinking ice by a lucky accident of chemistry. But the stability we take for granted is not guaranteed. By understanding the profound importance of something as simple as why ice floats, we gain a deeper appreciation for the fragile nature of our planetary home. It's a world built on a knife's edge, a world of beautiful, improbable, and life-giving exceptions. And it's the only one we have. How water breaks the rules of science. What we see around us feels normal. The ground, the sky, the substances we interact with every day. They follow a set of familiar patterns. But sometimes, the most familiar things are the most unusual. The water in this glass, a substance so common it barely registers in our thoughts, does not behave like the others. And in its quiet refusal to conform, it has allowed for a world where we can exist to think about it at all. This sounds like an overstatement. But it is not. Life exists on this planet because of a subtle property, a gentle departure from the expected that happens in every drop, every river, and every ocean. We see it without noticing. An ice cube in a glass floats. It is so ordinary that we dismiss it. But in that simple fact, a profound truth is hidden. A truth that separates our living world from a countless number of frozen, barren planets. Because according to the general patterns of the universe, that ice cube should sink. For almost any other substance, the solid form is denser than the liquid. But water does not follow. Today, we are going on a journey. Not to a distant star, but deep inside a single water molecule. We will explore the quiet arrangement that allows water to operate on its own terms. We will see how a tiny bend in a molecule becomes the architect of our entire biosphere. This is a story about the quiet strangeness of the most common thing we know. The familiar pattern that water ignores. To appreciate the quiet strangeness of water, we must first understand the pattern. It is a simple principle of temperature and energy. When you heat a substance, its particles move faster. They push each other apart. The substance expands. When you cool it down, the opposite occurs. The particles slow, they move closer together, and the substance contracts, becoming denser. This is the normal, predictable behavior of matter. A liquid, when it drips and cools, solidifies into a hard, dense form that would sink if dropped back into its molten state. This happens because molecules in a liquid are close but disorganized, like a crowd of people milling about. When that liquid freezes, the molecules slow down and lock into an ordered arrangement. For most substances, this fixed structure is more compact, more tightly packed. The same number of molecules takes up less space. The solid is denser. The solid sinks. This pattern applies to countless materials. It applies to simple elements and complex compounds alike. From mercury to wax, the story is the same. Freezing means contracting, and solid means sinking. This is the baseline. It is what we expect to happen. And then, there is water. Water seems to follow a different logic. As it gets colder and turns to ice, it does not contract. It expands. It pushes outward, becoming less dense. This is not a small deviation. When water freezes, its volume increases by about 9%. This is why pipes can burst in winter, and why freezing water can crack solid rock, a slow but powerful geological force. This simple act of expansion, this departure from a nearly universal pattern, is the starting point of our exploration. To understand it, we must leave the world of our senses and enter the invisible realm of molecules, where a particular shape and a special connection change everything. The anomaly in your glass. Let us return to that image, an ice cube floating in a glass of water. We have established that this is unusual. In a world where water behaved like most other substances, that cube of solid H2O would be at the bottom. The fact that it floats is a direct consequence of its lower density. The density of liquid water is about 1 gram per cc. Ice has a density of about 0.92 grams per cubic centimeter. It is lighter for the space it occupies. And so, it floats. This property is so deeply ingrained in our experience that its significance can be missed. But the strangeness goes deeper. It is not just that ice is less dense than water. The entire process of how water cools is peculiar. For almost every other liquid, as you cool it, it becomes steadily denser until it freezes. Water follows this pattern, but only to a point. As water cools from room temperature, it does contract and become denser. But then, at 4 degrees Celsius, something changes. It reaches its point of maximum density. If you continue to cool it from 4 degrees Celsius down to its freezing point at 0 degrees Celsius, the trend reverses. The water begins to expand again, becoming less dense. This is known as the anomalous expansion of water. This behavior is deeply counterintuitive. And it has colossal consequences. In a lake during autumn, as the surface water cools, it becomes denser and sinks. This pushes the warmer, less dense water from below up to the surface, where it too is cooled. This circulation continues until the entire lake, from top to bottom, has reached a uniform temperature of 4 degrees Celsius. Only then, once the entire body of water is at its densest, can the surface cool even further. As the surface water drops from 4 degrees Celsius toward 0 degrees Celsius, it becomes progressively less dense. Because it is now lighter than the 4 degrees Celsius water below it, it stays on top. When it freezes, the resulting ice, being about 9% less dense still, forms a solid layer that floats on the surface. This is a life support system. The floating layer of ice acts as an insulating blanket, protecting the liquid water beneath from the cold air above. This barrier dramatically slows further freezing. It ensures that even in harsh winters, lakes and rivers do not freeze solid from the bottom up. Underneath the frozen surface, a world of liquid water at a stable 4 degrees Celsius persists. It allows fish, plants, and countless other organisms to survive until spring. Without this two-part anomaly, life in any body of water that experiences winter would not be possible. The question then becomes, what is happening at the molecular level to orchestrate this? The answer lies in its shape, its charge, and a unique kind of connection that allows water to follow its own quiet path. Deepening the mystery, the molecular dance. To understand water, we must shrink down to the molecular scale. The water molecule, H2O, is simple. One oxygen atom bonded to 2 hydrogen atoms. Its significance lies not in its parts, but in its geometry. The bond between oxygen and hydrogen is covalent, meaning they share electrons. But this sharing is unequal. The oxygen atom is more electronegative, it pulls the shared electrons closer. This creates a region of slight negative charge around the oxygen, and leaves the 2 hydrogen atoms with a slight positive charge. This creates a polar molecule. It acts like a tiny magnet. But there is another critical detail. The molecule is not a straight line. The 2 hydrogen atoms are bent into a V-shape, at an angle of about 104.5 degrees. This bent shape is essential. If the molecule were linear, its polarity would cancel out, and it would be a very different substance. Because of its polarity and shape, water molecules are attracted to one another. The positive hydrogen of one molecule is drawn to the negative oxygen of a neighbor. This attraction is called a hydrogen bond. A single hydrogen bond is much weaker than the covalent bonds within the molecule itself. It is more like a temporary connection than a permanent weld. But their power comes from their number. Each water molecule can form up to 4 hydrogen bonds with its neighbors. This creates a dynamic network. In liquid water, this network is a fleeting, chaotic dance. The molecules have enough energy to move constantly, so these hydrogen bonds are continuously forming, breaking, and reforming. The molecules remain close, held by these transient connections, but they can still slide past one another. This gives water its fluidity. They are packed together, but without any long-range order. This web of hydrogen bonds is the source of many of water's other unusual properties. It is why water has a high boiling point and can absorb a great deal of heat. Much of the energy added to water goes into disrupting these connections. But the most profound effect of these hydrogen bonds occurs when the temperature drops. As the molecules lose energy, the dance slows. They begin to arrange themselves into a more permanent, stable configuration. This is the moment of freezing. And it is here that the 104.5-degree angle of the water molecule performs its most significant act. The quiet arrangement, the crystal lattice of ice. As liquid water cools toward freezing, the molecular dance slows to a gentle sway. The hydrogen bonds last longer. The molecules begin to lock into place. To satisfy the demands of forming 4 stable hydrogen bonds, the water molecules must arrange themselves in a very specific way, dictated by that 104.5-degree angle. The most stable, lowest energy configuration is a tetrahedral arrangement. As molecule after molecule snaps into this formation, a vast, 3-dimensional crystal lattice emerges. The structure is an incredibly ordered, repeating pattern of open, hexagonal rings. Think of it this way. In liquid water, the molecules are like a disorganized crowd, close together but constantly shifting. Now, imagine everyone in that crowd must hold hands with 4 other people, but their arms are locked at a specific angle. To do this, everyone has to spread out, creating a more open, spacious formation with gaps in between. This is what happens when water freezes. The rigid, angled demands of the hydrogen bonds force the molecules farther apart than they were in their liquid state. The result is an airy, crystalline structure full of empty space. The mass has not changed. We have the same number of H2O molecules. But because of this open lattice, they now occupy about 9% more volume. Since density is mass divided by volume, an increase in volume with the same mass means a decrease in density. The reason ice is less dense than liquid water is that its solid structure is paradoxically full of empty space, a direct result of the geometry of the water molecule. This is a reversal of the normal pattern. Most substances pack more efficiently when they solidify. Water packs less efficiently. When ice melts, this rigid structure collapses. The hydrogen bonds break, and the molecules fall into the empty spaces, moving closer together. This is why the volume decreases and the density increases as ice turns to liquid. As the liquid is heated from 0 degrees Celsius to 4 degrees Celsius, this collapse continues, and density increases. Above 4 degrees Celsius, another effect takes over: thermal expansion. The molecules start moving so fast that they push each other apart, and density begins to decrease again, just like a normal liquid. The density of water is a quiet balance between 2 opposing forces. Below 4 degrees Celsius, the formation of open, ice-like structures dominates. Above 4 degrees Celsius, the kinetic energy of the molecules dominates. The peak density at 4 degrees Celsius is the point where these 2 effects are perfectly balanced. This is the mechanism that underpins the survival of our planet's aquatic ecosystems. The tiny 104.5-degree bend in a single molecule, when multiplied trillions of times, creates a substance that behaves unlike almost anything else. A substance that, by following its own rules, creates the conditions for life. A unique substance. It is tempting to think of water as entirely alone in its behavior. The specific act of expanding upon freezing is not, strictly speaking, exclusive to water. A handful of other substances also become less dense when they solidify. Elements like silicon, gallium, and bismuth exhibit this same tendency. Their solid forms organize into spacious crystal structures that are less compact than their disordered liquid states. So, if other substances do this, what makes water so special? The answer is context and consequence. While silicon and bismuth are interesting materials, they play no significant role in the fundamental processes of life on Earth. Water is unique not just because it expands, but because of what it is: the solvent of life, the medium for biochemistry, and the most abundant liquid on our planet's surface. None of the other substances that expand when they freeze are liquids under the normal range of temperatures on Earth. Water, by contrast, exists naturally in all three states: solid, liquid, and gas, within our planet's climate. It is the liquid that fills our oceans, the solid that forms our ice caps, and the gas that creates our clouds. Therefore, while the physical mechanism might have other practitioners, the implications of that mechanism are unique to water. The fact that solid bismuth would float in liquid bismuth has no bearing on global climate or the survival of a species. The fact that water ice floats on liquid water is arguably the single most important physical property for the existence of life on this planet. Its quiet rebellion is a planetary-scale engineering feat. Its uniqueness lies not in the act itself, but in the profound, life-giving consequences of that act. A world without the anomaly. We have explored the secret of water's behavior. Now, we can ask the most important question. What if water behaved normally? What if solid H2O was denser than its liquid form? It is a small change to a single physical property. The consequences would be immense. Imagine a lake on a world where water follows the familiar pattern. As winter approaches, the surface water cools and becomes denser. Without the 4 degrees Celsius turning point, it would simply continue to get denser all the way to its freezing point. The coldest water would sink to the bottom. When the surface water freezes, the resulting ice, now denser than the water around it, would sink. It would drift down and settle on the lakebed. The newly exposed surface would then cool, freeze, and sink as well. Layer by layer, from the bottom up, the lake would turn to solid ice. In summer, the sun's warmth would only melt the topmost layer. The deep ice at the bottom would be insulated by the water above it. Year after year, the process would repeat. Over time, every lake, river, and eventually the oceans themselves would freeze solid. Our planet would become a world of ice. The oceans would be vast, solid plains. The entire climate system, which relies on deep ocean currents to distribute heat, would collapse. And life as we know it would be impossible. The cradle of life was the ocean. In a world of sinking ice, that liquid environment would not exist. There would be no refuge for aquatic life. The evolutionary path that led from microbes to us would have been severed before it began. Even during Earth's most severe ice ages, the insulating blanket of floating ice allowed liquid water to persist, a sanctuary where life could endure. Our world is a water world not just because water is abundant, but because it behaves in this one, specific, anomalous way. The tiny kink in the H2O molecule is magnified across the entire globe. It ensures our planet has stable, liquid oceans. It shelters life. It moderates our climate. Every time you see ice floating, you are witnessing the signature of a habitable planet. More than just ice. The density of ice is water's most spectacular departure from the norm, but it is not its only one. The same molecular architecture, the polarity, the bent shape, and the network of hydrogen bonds gives water a whole suite of other quiet abilities that are just as crucial for life. First, consider water's ability to absorb and store heat. It has a high specific heat capacity. This means it takes a large amount of energy to raise the temperature of water. Again, the reason is hydrogen bonds. When you add heat, much of the energy is used to disrupt these connections, rather than directly increasing the temperature. This property is vital for regulating Earth's climate. The oceans absorb enormous amounts of solar heat, then release it slowly, preventing extreme temperature swings. It is also what helps our bodies maintain a stable internal temperature. Next is water's high heat of vaporization. It takes an extraordinary amount of energy to turn liquid water into a gas. This is why sweating is such an effective cooling mechanism. As sweat evaporates, it draws a large amount of heat energy from our bodies. Finally, there is water's role as the universal solvent. Its polarity makes it incredibly effective at dissolving other polar and ionic substances. This allows water to transport vital nutrients in the soil, in our bloodstream, and inside every cell. Blood plasma, mostly water, carries dissolved nutrients, hormones, and gases throughout our bodies. Cohesion and adhesion, the properties that allow water molecules to stick to each other and to other surfaces, are also results of hydrogen bonding. They create surface tension and enable capillary action, the process that helps water travel up the stems of plants, defying gravity. Each of these properties is a direct consequence of hydrogen bonding. They are all part of water's unusual nature. Together with the miracle of floating ice, they form a suite of finely tuned physical properties that seem almost designed to support a complex and thriving biosphere. We began with a simple observation: ice floats. We have journeyed through thermodynamics, into the molecular world of liquid water, and before the crystalline structure of ice. We have seen how a single detail of molecular geometry, a 104.5-degree bend, gives rise to a cascade of life-sustaining properties. Water does not follow the expected script. In a universe that favors contraction upon cooling, water expands. In a world where solids are usually dense, water's solid form is light and buoyant. This isn't a violation of law. It is the following of a different, more intricate law, one that makes our world an exception. This singular behavior prevents our oceans from freezing solid and creates a haven for life in a largely hostile cosmos. The story of water is a quiet lesson. It suggests that the most profound truths are often hidden in the most familiar places. We look to the stars for signs of life, searching for worlds where liquid water might exist. But the true miracle is not just the presence of water, but its peculiar nature. Its strangeness is its genius. So the next time you drop an ice cube into a glass, take a moment. See it not just as a way to cool a drink, but as a testament to a beautiful and life-giving anomaly. You are witnessing the quiet departure from the norm that transformed a barren rock into a living world. The deepest mysteries are not always far away. Sometimes, they are floating right there, in a simple glass of water. If this quiet exploration into the world of water helped you see something familiar in a new way, consider liking the video and subscribing to the channel. We explore the world's quiet wonders each week. And if there is another everyday phenomenon you feel holds a deeper story, feel free to share it in the comments below. Thank you for watching.